We have a 4 day talk test for free. So maybe that's the business we got. Ah, since the SEM proceedings are not ready yet. Whose fault is that?
Check them.
The proceedings, they're not ready yet. They just ask us the papers. Yeah, yeah. It looks great. Because I sent the PDF that I wanted to take the chair. The chair asked me the PDF and I sent the good one. This coffee tastes like cinnamon. Did you get this coffee? Do you get it?
In the smell, it smells, but in the smell, I can see.
It's just a smell? I was like, what is this? And then you start working. I'm gonna start this. Okay. Okay, let's get started. Welcome everyone to this second workshop on memory-centric computer systems. Before everything, all the materials that I'm going to present or the presenter is going to cover over here is available in our website. You can download and follow up during the program. And also we are live streaming the program on YouTube, and the recordings are going to be available online if you want to revisit the materials any given moment in time. So thank you everyone for joining this early and in this Sunday. I am the main organizer of this workshop. My name is Geraldo. I'm a just graduated PhD student from the Safari Research Group, advised by Professor Onur Mutlu, and I've been working on the subject of memory-centric computer systems since 2017. Together with me, I have several of the organizers, as Dr. Mohammad, Ataberk, Olgun, and Professor Onur Mutlu, of course. Unfortunately, he couldn't be here today, but I will do my best to cover his materials as good as I can. So this is the agenda for today. We have a quite extensive agenda throughout the entire day. Here in the morning, we are going to give some overview of the concept that you're going to cover. So what is memory-centric computer systems, why it's important, the two types of processing in memory architectures, processing using memory and processing in memory. And then in the morning as well, we are going to have a talk from one of our PhD students, Ismail, that is going to join remotely, that is going to talk about our advances on using DRAM chips as they are to perform computation without any modifications to the system. And then in the middle, we're going to have a coffee break and also a lunch break. And then in the afternoon, we're going to continue. We're going to have an invited talk from Dr. Constantina, which is over here. She's going to talk about PIM architectures for bioinformatics. And we are going to have a coffee break, and then we are going to have two other invited talks. And then finally, three other invited talks. And then you're finally going to conclude. If you are so eager to learn more about memory-centric computer systems, we are going to have a third version of this workshop happening very soon in ISCA in Japan. Over there is going to be a half-day workshop, so it's going to be a shorter version of this workshop. But again, all of the materials and the recordings are going to be available online. So this is just a brief logistics of the workshop, and then we are going to start with the first talk. Let me just do a quick context switch. Okay. Okay, so feel free to, I talk a lot, so feel free to stop me at any given moment in time to ask questions. From time to time, I might also stop to see if there is any question on the YouTube live stream. So let's start with what is memory-centric computing, why we are here. So you might know this already, but computing is mostly bottlenecked by data in today's systems. And this is very important today because data is key for many applications. In the past, we were using a lot the genomic example, but nowadays it's very easy to justify this statement since the height of generative AI, where as much data you put into the model, the more performance the model is going to provide in different metrics. So data is very important, and the amount of data that the applications are consuming and generating is significantly increasing over the generations. I gave the example for generative AI, and this is just one example from a talk from Grok. So over here in the x-axis, we have the model memory footprint, and then y-axis, you have the training compute, and then you have the different models all the time. So since the realization of the first BERT model, which has around 110 million parameters, ChatGPT-3, which is already an oldish model, significantly increase the number of parameters in the memory footprint required for such neural network models. So in the end, we had more than 3 orders of magnitude growth in the memory demands for such generative AI models in the span of only 2 years, and the trend is not stopping. So this is not only true for generative AI. So other application domains, for example, bioinformatics, suffers from similar issues where applications highly depend on the size of the genome that you're actually sequencing or trying to extract information from. So in the end, the main thing that is important is that generating and consuming data significantly impacts key metrics in the system, not only performance, but also energy and sustainability. So powering up such data centers that perform these computations become more and more problematic. And in the end, we want a world that looks more or less like this, that does not burn much carbon footprint, or a world that actually requires burning a lot of power in order to perform such computation. So in the end, what we want in the future is systems that are high performance, high energy efficient, and sustainable, and all of those at the same time. However, as I mentioned, accessing data in current systems becomes a key performance and energy bottleneck. And this is happening because of the way that we have been designing systems in the so-called von Neumann model. I'm going to come back to this later on. So we design systems, of course, not deliberately, but in a way that our design significantly wastes energy and also performance. And the main reason is because the way that you're designing systems is in a way that computation is performed very far away from the data itself, in a process-centric way. So as I mentioned before, the von Neumann model dictates that we design systems by dividing the systems into 3 different portions: computation, communication, and memory and storage. And we are very good at designing systems that heavily optimize the computing engine. So at every generation of CPU, GPUs, FPGAs, we are targeting more and more tera operations per flop, for example. We're also getting better at designing communication to move data around in the system, but still the way that we design in memory is in a very passive way, that the main metric that we are looking for is storage per dollar. And this does not help on achieving that goal of improving performance and energy efficiency. So if you look at how this design have evolved over the years, we are going to see a huge imbalance on what is the real state that we have in the system for computing versus the real state that you have in the system for storing and moving data. So this is an old example from a processor at the time of Professor Onur's Mutlu PhD defense. And here, what you can see is that the red part is the part in the CPU SoC that performs computation. And all of the green part here is dedicated either to store data or to move data. Yet our system is mostly bottlenecked by data, even though there are a lot of the real estate that you are using to store data compared to versus doing computation is still you are being bottlenecked by data movement bottleneck. So if you look at modern processors, we see that this trend just continues. So this is an example here from AMD Razor processor, and the area here in green again is all dedicated to L3 caches and L2 and L3 caches. So the majority of the real estate of this processor is also dedicated to storing data. This is also true for future for more advanced process integration models that uses 3D stack integration to realize larger cache hierarchies. Still, large portions of the system is dedicated to storing data, and this just moves over time. So the way that we are being designing systems to try to avoid such data movement bottlenecks that I mentioned before is to putting more and more SRAM into the system. So this is what you are seeing over here in these images. In the ends, this is a picture of the Apple M1 processor. We cannot even see from the picture of the OC which portions is actually dedicated to processing, because memory itself is significantly taking the space that requires in the SoC to store data. Here in this picture, even you cannot see the space that takes for storage is over here in red, and in green here we have the space required for embedded DRAM, and in the middle a lot of SRAM area. So even though we have been designing systems to store a lot of data, data still overwhelms current machines, significantly impacting robustness, energy, and performance, and of course, costs. So this is not a new problem. Research sites have this paper called "It's the Memory Stupid," published in 1996. That back at that time, he already foreseen that the design of the memory subsystem would be the only important design used for microprocessors, because he was already foreseeing this discrepancy between the amount of power that computing can have and the impact of moving data in such processor systems. So if you look at how this impacts real applications themselves, we can see that this is an example here from aggregated across hundreds of applications that at the time that of the publication, 2003, Intel was using to manufacture their processors or to benchmark their processors. And as you can see here, the majority of the CPU cycles for those workloads were spending on moving data. At the time, there was no L3, so the last level cache was the L2, and more than 50% of the execution cycles were dedicated to moving data from the last level caches. And this does not get better. So this is an example from Google themselves. They did this experiment on their data centers where they tried to classify the where the execution cycles for key workloads running their data centers were going to. And as you can see here, this reddish part here is back-end cycles. So cycles dedicated to memory access. So even in data centers, a significant portion of the execution cycles were taken by memory. So, and why this is happening? So why data is a major bottleneck for both performance and energy consumption in current systems? And again, is because of this discrepancy that was generated over the years for computation versus memory. So this is just an example from Dali from HiPeak 2015, where he shows that a memory access consumes more than 2 to 3 orders of magnitude the energy to perform a complex double precision operation. And this is just another view of the same data. So here I have the energy normalized for a 32-bit operation versus accessing different places of the system, like the register file, multiplier, SRAM cache versus DRAM. And you can see here that, again, a memory access consumes 3 orders of magnitude more energy than simply doing a simple addition in your processor. So just more data to try to bring this problem home. We did this experiment together with Google to show that it was not only big data centers that were suffering from data movement problems. We look at consumer workloads that runs on Google Chrome at the time, and we saw that from those workloads, 62.7% of the total system was spent on data movement bottlenecks. And over here is even a bigger problem, because such consumer systems are very power sensitive, because you have a battery that's going to run off over the time. And if you look at specialized machine learning accelerators, again, this is work that we did together with Google, where we analyzed their Google Edge TPU accelerator. We saw that for some neural network models, the majority of the system energy was spending on moving data back and forth to this accelerator. And again, this is because of the way that the system was, the current systems have been designed. So basically, we need to a paradigm shift that allow us to break these data movement bottleneck issues, both in terms of performance and energy efficiency. So right now, computation is performed very far away from the data, but we need to move to a paradigm shift where we can do computation while minimally moving the data across the SoC, and hopefully do computation where it makes sense, so where the data resides. So if my data is in this SoC here, and my data is in my storage or in my DRAM, there is no actually reason for me to have to bring the data all the way from the storage to the processor core in order to perform a computation that likely is going to be very minimal. So our goal here is to have a processing capabilities inside the memory chip themselves, so I don't need to move data around to a centralized CPU. So our goal here is we have your application, and then when the processor simply needs to do operation, instead of just loading the data from memory, just query the memory, like memory do this carry scan on my database for me, or generate this GenV operation for this neural network model. And then the memory simply return the result. So this is a very nice paradigm and a very nice idea, which is not particularly new. But to do that, we have to answer many questions that during this workshop, we are going to try to answer. So for example, how much computation should I put in my memory? So in the end, we don't want to embed out of order CPU or GPU inside my memory chip, because that would create power dissipation problems and also reduce the density of my memory chip themselves. So there is a trade-off over there. So what is the minimum amount of computation that I can put inside my memory chip in order to achieve high performance and high energy efficiency? How I communicate across memory chips inside the processor chips inside the memory chip? What is the software and hardware interface that allows me to query this memory? And how do I need to change system software compilers and language for this to work? So basically what I'm trying to convey here is that even though this idea is quite simple on paper, just put computation in your memory chip, doing so significantly involves revisiting several of the different layers of the computer architecture stack. But we're going to try to do so and highlight how this can be done in current systems during this workshop, one problem at a time. So as I mentioned, this idea to move computation nearby the memory is not new. The first work that we are aware of that proposes this idea of processing near or near memory is from 1969, cellular logic memory arrays. And there was also a follow-up idea from 1970, a logic memory computer, where again, the authors proposed to move computation nearby memory arrays themselves. So why today is a good time to do processing memory if this idea has been proposed many years ago, and we are not like your laptop or your phone does not necessarily have such realization of such system yet, right? So there are several reasons. The first one is technology scaling. So there is a huge problem right now with memory scaling. I'm going to highlight this in the follow-up slides. But basically, the smaller and the denser that we make memory chips, particularly DRAM, for example, the more prone to reliability and robustness issues that those memory chips become. So I'm going to talk about redisturbance in the follow-up slides. But it's not only true for DRAM. SRAM also have a scaling barrier, and this is the same for flash chips or storage chips. Also, as I mentioned earlier in this talk, there is a huge demand from the application level now for more performance systems, and those applications are highly bottlenecked by data movement. So if we don't rethink the way that we are generating systems for such architectures, we are going to end up on the same data movement bottlenecks that I just mentioned before. At the same time, we are designers are squeezed in the middle. So if you keep trying to design systems as we are designing over the follow-up years, we are going to try to design systems that are high performant but suffer from data movement bottlenecks at the same time where I'm going to be suffering from memory technology scaling for such data-intensive workloads. So disclaimer, I just mentioned, I'm going to do a detour, as I mentioned earlier, about memory redisturbance. And then there is this phenomena quite well known right now that one can predictably induce errors in most DRAM chips today. And this event is called row hammer. Not only row hammer, there is also row press, and I'm going to talk about them briefly. This is just to highlight the memory scaling problem that I just mentioned before. The main idea here of row hammer is that by activating, I don't have this slide here, but by accessing consecutive rows inside the DRAM chip, inducing blitz flips in nearby DRAM rows. So one can use such blitz flips to, for example, take control of a system or to leak key information from the DRAM memory chip. And memory manufacturers are aware of this issue, and they are trying to implement more intelligent memory controllers in order to mitigate such disturbing problems. So this is an example from a work from SK Hynix, where they are adding some counting inside the DRAM chip in order to count how many times a row is being accessed and try to avoid accessing a row as many times in order to avoid a row hammer bit flip. I don't have it here in this slide, but it's also important to highlight that this has become such a big problem that the memory consortium that generates standards for DRAM, JEDEC, right now included in its latest documentation or the latest specification already solutions that mitigate row hammer bit flips in future DDR5 chips. But it still works from academia have shown that those solutions are yet not bulletproof. So we don't expect this reliability issue from DRAM chips to go away anytime soon if you don't rethink the way that you're designing systems. Also, other than this memory scaling problem for memory chips, there is a nice manufacturing push in order to design more intelligent memory chips themselves, especially based on 3D integration. So back in 2012, there was this hybrid memory cube consortium, does not exist anymore. But basically what they have in the consortium was a 3D stack architecture where we have many layers of DRAM chips interconnected with a logic layer that allows for computation. So even though this does not exist anymore as in the hybrid memory cube consortium, now we have HBM, hybrid bandwidth memory chips themselves that operate very similar to this organization. And in the next generation of HBM4 chips, we already expect to have processing memory capabilities in the logic layer of the chips themselves as per the specification. And of course, it's not only 3D stack memory that allows for this type of computation. We are going to see later on in the workshop developments from industry of such systems. This is just to highlight that the landscape of memories that are also capable of doing computation is increasing as the memory manufacturing process for memory gets more and more developed. So we have examples from startups like Upman, big memory manufacturers like Samsung and SK Hynix, and also cloud providers like Alibaba, all of them designing SoCs where we have memory coupled with some computing capabilities. We are going to see more examples of those later on today. There are also advancements in interconnect networks like CXL memory expander that allows for easier integration of computation together with memory. This is just again an example here for a CXL based memory solution that that also adds computation nearby the memory card itself. And then Samsung again have been showcased their prototypes for such architecture. And again, we are going to see more details on those during this workshop today. So this is just an overview of the field of memory-centric computing, and hopefully now you're motivated why it's important to start doing computation near the memory chip themselves. And just as a highlight, in case you want to learn more about memory-centric computing systems, and you're going to be, if you're just bored of hearing me talking about it, you can just read it for yourself. We have this very nice summary book chapter called Multiplying the Processing Memory, where we discuss several of the issues that I mentioned here and going to mention here today. We also have lectures online that covers process memory architectures, and they're available on YouTube, and also lectures on other memory systems like SSD-based systems that also cover relevant subjects that we are going to cover here today. So we have been conducting these PIM workshops and tutorials for the past 2 years in many conferences. All of the materials are available online. And as I mentioned before, we have the follow-up one coming in ISCA at the end of this month. So the way that we need to approach this workshop is with open mind. So many things that I'm going to discuss here, you might scratch your head and say like, oh, it's not going to work, or this is too complex to be deployed in current systems. But we are not designing systems for 6 months or 10 months. We are looking in the future and seeing how we can design more efficient systems in the span of 2, 3, 5 years. We need to think, so you need to do that. We need to think differently from past approaches. Some quick taxonomy that we are going to use towards this workshop. I mentioned this idea of processing in memory. So those are memory chips that have computing capabilities. And we are going to further divide those architectures into 2. Processing using memory, which are going to use the analog operating principles of the memory cells themselves to perform computation, and processing near memory, which are similar to how we were designing systems today, where you're going to embed logic inside the memory chip themselves. As I mentioned, the nature of the computation dictates if it's using memory or near memory. I'm going to mostly highlight the advantages here on DRAM, since it's the main memory manufacturer technology for current systems today. But several of the ideas that I'm going to illustrate over here are also applicable to other memory manufacturing, memory technologies, such as flash, SRAM, VRAM, and so other non-volatile memory chips themselves. Also, the location where the computation is going to be placed might vary. We can add computation nearby storage. We can also add computation nearby a disk, SSD, a main memory, a cache, a register file, memory controller, interconnect as needed, depending on where the bottleneck for that particular application is generated. So you can think about those process memory architectures as a tuple of 3 different PIM types. The nature of the computation, the technology that is being used, and the location where the computation is going to be embedded. And also, over of this talk, we are going to focus on 1 or 2 different types of PIM architectures, but you don't need to think about one versus the other. So all of those architectures can be combined in a single system for a more holistic end-to-end design. So you can have a processing engine in your cache hierarchy, while also in our DRAM and also in the flash chip, for example. We are going to start very simple over here. So basically, we are going to treat our main memory as a specialized accelerator, where we are going to offload some computation to such accelerator itself. And the next slide, I'm just going to highlight one of such tuple of processing memory. It starts with what we call processing using DRAM. So here we are going to use DRAM cells in order to perform computation inside the main memory of the chip itself, in an architecture that we call processing using DRAM. We are going to start very simple. What I'm going to show next might look a little bit like magic because I didn't give the background, but it's just to illustrate what's possible. So let's say that I want to perform in DRAM, I want to copy one row or one array in your system to a different array in your system, but without involving moving data to the CPU. So I just tell my memory, copy array A to array B and be done with that. Also, let's say that I want to tell my memory, perform a bitwise AND operation of our array of thousands of elements and return the result. So we can do that, and turns out in current DRAM chips themselves. This is what the next talk later on from Ismail is going to mention. And by doing so, we can have significantly performance and energy improvement because we are not moving data to a very narrow memory channel, at the same time that we incur very low or minimal hardware costs to the system themselves. So basically, what we want or what we are going to start doing is this simple data copy initialization routine, which is used actually in many applications. Like, for example, when you're forking threads or you need to do a checkpoint for a database, such data copies are quite frequent operations. Turns out that in Google, across all of its data centers, 5% of the cycles for Google data centers is actually due to memory move and memory copy operations. This number might look small, 5%, but think about 5% over all of the fleets of data centers that Google have. So that's a quite big number. So in today's systems, how such copy initialization is performed, right? So you have your CPU, you have your caches, you have your memory controller, you have your DRAM chip. So if I want to copy one row to another row, I need to move blocks of a row, cache line worth of blocks, through a very narrow memory subsystem, through the cache hierarchy, and eventually to the CPU. Then I move the destination row, again, cache line by cache line, through the cache hierarchy to the CPU itself, and then I perform the copy operation. And I repeat this cache line by cache line across all of the DRAM rows that are part of my memory object, right? This is a very high latency operation because I need to break down this operation in sub-blocks. This is also high bandwidth consumption operation because I need to move these pieces of data via a very limited interconnect that connects the main memory to the main SoC. Also generates cache pollution because I need to move the cache blocks from the source and the destination to the cache hierarchy, and also generates unwanted data movement. So to do this operation, to do a 4 kilobyte page copy via DMA, so I'm not even involving the CPU over here, it takes around 1046 nanoseconds and 3.6 microjoules. So if you don't have to design a system, and I ask you, what is the easiest way to move this white block here to the red block here? Why would you say so? Do you have any guess? What's the shortest path to do this copy? Just copy down. So I just want to tell my memory, this is the address, that's my source. This is my address, that is the destination. Just move the source to the destination, and then you'll be done with that. So there's no need to bring the data to the cache hierarchy to the processor. So this is low latency because I'm not bringing cache lines to cache lines through this limited memory subsystem, memory channel. I'm not using any external memory bandwidth. Generates no cache pollution because I'm not involved with the CPU, and does not generate any unwanted data movement. So if you do the computation like this, we can reduce the latency of this operation from 1046 nanoseconds to 90 nanoseconds, and reduce the energy that it consumes from 3.6 microjoules to 0.04 microjoules. And the way that this is can be realized is with this mechanism called row clone. The idea here is to activate or to access two DRAM rows back to back. So the first, this is going to make more sense when I give background on DRAM. But basically what this does is when you activate the source row, it brings the source row to a local row buffer that's available inside the DRAM chip. And then when I activated the destination row, the data that was latched in the local row buffer is copied to the destination row. So the idea here is to perform this back-to-back in DRAM row activations, which involves or does not add any hardware cost to the memory chip themselves. And as I mentioned before, and how we're going to see later on in this talk, this operation is not defined in your memory specification, but you can already do this operation in your DRAM chips themselves. The DDR4 chips are already capable of doing such in DRAM row copy operations. This, as I mentioned, significantly reduces latency and also significantly improve energy consumption. And you're going to see more of this later on when I get to the specifics. This is just some initial works that show that by violating DRAM timing parameters, we can actually perform such in DRAM row copy operations in commodity off-the-shelf DRAM chips. And we have an infrastructure that we are going to discuss later on also in details, the FPGA-based infrastructure that allows you to reprogram the memory controller and perform such in DRAM row copy operations. So this infrastructure is available online and is open source for you to play with. And again, we can significantly improve throughput by doing computation like that. In real, this data is for real DRAM chips without any modifications. So this is very nice. We can significantly improve this mechanism to do more interesting things. For example, copy data across different arrays in the DRAM chip, move data that finer granularities, cache line granularities, also do a better inter-bank data copy, and use similar idea to not only copy data, but also perform computation over data, which is what I'm going to mention next. Where is my slide? Over here. So if you follow the same idea that I just mentioned before of activating multiple DRAM rows at the same time, we can perform in DRAM and OR operations and on modifying DRAM chips. So when we activate 3 DRAM rows at the same time, so we have here row A, B, and C, the data of these rows are going to perturbate the local bit line, which is connected to this line here at the same time. And the sense amplifier is going to sense this perturbation and amplify the difference to the majority of the data stored into the DRAM cells themselves. So here we have 2 cells storing logic 1 and 1 cell storing logic 0. And the majority of this is going to be a logic 1. And in the end, you're going to have this output, this majority 1, stored in the 3 DRAM cells that was activated at the same time. So by controlling one of those rows, we can actually perform OR and AND operations, depending on the data that is stored in row C, in a book bitwise manner. This is going to make more sense again when I get to the details of this. But basically, such operations are such book bitwise and OR operations are quite common in many application domains, such as database or DNA sequence mapping, for example. And by doing this computation in the DRAM chip themselves, we can significantly improve performance for such applications and also improve energy consumption. So this was Mbed. This is just some reference. And so, okay, very nice. We can do in DRAM row copy with row clone. We can do in DRAM book bitwise and the NOR operations with Mbed. But what about more complex things like addition, for example, right? Or a multiplication or a division? How can I do such operations that you might actually write down in C in your DRAM chip themselves? So to answer this to answer this question, we propose the SIMDRAM framework, which composes a sequence of those in DRAM row copies and in DRAM Boolean operations in order to realize in DRAM arithmetic operations. So this is, I'm going to get more details on this later on, but basically what we do is we take a desired operation like a RIP carry header. We convert this operation into our efficient majority of 3 representation of the same operation. And this is required because what we are doing when you are doing multiple row activations in DRAM is a majority operation. And then we map such majority graph into sequence of in DRAM row copies and in DRAM triple row activation. And then during the execution, the programmer triggers the one of those operations like in DRAM addition, and then the memory controller transparently issues the required operations to the DRAM chip in order to realize such operations. So we use this framework to implement 16 complex in DRAM operations, in DRAM additions, multiplications, divisions, subtraction, machine learning primitives like ReLU, for example. And we use those 16 complex operations to accelerate 7 commonly used real-world applications, including database and neural networks. And by doing computation in DRAM, we see significantly improving throughput and energy efficiency, and also performance for those 7 real-world applications. So those were SIMDRAM, and we keep improving the substrate. I'm going to talk about MIMDRAM later on here, But the main problem that we have with the way of doing computation that I just mentioned before is that the granularity of computation is very large. So it's depending on the size of your DRAM row, which is thousands of columns, 65,000 of columns. And how many times you write a loop that has 65,000 elements or goes through multiples of 65,000 elements, right? It's not very common. So if you want to actually accelerate real applications, we need to break down this computation into more tangible granularities for computation. And this is what we do in this MIMDRAM work, which I'm going to mention in more details later on. So this is all very nice. We can do in DRAM row copy, in DRAM majority, in DRAM arithmetic operations. But there is a class of operations that are called transcendental functions. Think about sine, cosine, logarithmic operations that are very costly to approximate using arithmetic operations. In order to do those operations in DRAM, we use lookup tables, which is a very old idea, but we can do that in DRAM chips in order to achieve very high throughput. This is the work that we do in Pluto, and we are going to see more details later on over here. In DRAM, operations are very powerful and are not limited for arithmetic or transcendental functions or in DRAM row copies. We can also do security primitives. For example, puffs or physical unclonable functions using DRAM chips themselves, and also generating two random numbers by violating DRAM timing parameters. This is just the work that we did with a framework that can be used by many applications that rely on two random number generation. So as I mentioned, commodities off-the-shelf DRAM chips are already quite capable of doing these operations, and we are going to have a talk later on highlighting such developments by Ismail. So yeah, those is the work that we are going to see later on. And over there, we are going to see that current DRAM chips are capable of performing NOT operations and also 16-input NAND or NOR operations, again, without any modifications to the DRAM chip themselves. I'm not going to get into details on this because Ismail is going to cover all of that. So I'm talking a lot about DRAM over here, but as I mentioned earlier, all of those developments are not limited to the DRAM chips themselves. Other memory technologies, for example, flash, are also capable of performing multiple sensing of many rows inside a plane in order to perform bitwise operations. So basically, by doing such multiple sensing operations inside a flash device, again, you can do this in current flash chips. You can perform bitwise AND operations and also bitwise OR operations, which is not here. At very high reliability. And by doing that, we can significantly improve storage bound applications as database operations, for example. And this is the work that we did in Flash Cosmos. So other memory memory technologies, such as emerging memory volatile memories like ReRAM, resistive RAM, or phase change memory, are capable of doing even other operations like constant time in DRAM multiplication operations. And there's a lot of startup right now looking into those technologies in order to accelerate machine learning operations, because they can perform math multiplication at constant time by using Kirchhoff law. So those are those works that initially provide the realization of such implementations. So this is I already mentioned. And right now I was mentioning processing using memory operations, right? Those architectures which use the analog operating principle of the memory themselves to perform computation. So let's look at the example of processing near memory operations. So let's say that we have a graph processing algorithm like a PageRank, that what it does basically is traverse a graph and does some multiplication and some increment of a variable. So if you do this operation in current memory chips, you're going to end current CPU chips. You're going to end up at very frequent random access because I'm traversing a graph. At the same time that we have a very little amount of computation for your CPU to operate over. It's basically a multiplication and addition. We can use 3D stack memory devices to embed logic to the logic layer of such engines in order to perform communication of graphs and also computation of the of when you traverse each one of the graphs for the page rank algorithm. And by doing so, we can significantly improve the memory throughput of your system and accelerate graph processing workload. And we are going to, again, just a highlight, we're going to see more details on this later on. This is not limited to graph processing. We can do similar operations on set-centric architectures, also neural networks, which I'm going to highlight over here. So this is just some work that we did together with Google, where we analyzed 24 different neural network models from them. And then we saw that those models have significant variation in their characteristics per layer. And also even inside the single model, different layers experience different characteristics that might impact the hardware design, as for example, Mac intensity and reuse. But the way that we are designing neural network accelerators is in this monolithic way. Where we have different layers with different properties targeting a single monolithic accelerator. This generates super performance and also throughput and energy waste. Our work proposed to have smaller accelerators that are either tailored for compute or tailored for memory access by adding logic inside the 3D stack, the layer of a 3D stack memory chip. And by doing so, we can map those different layers of a neural network model to either compute-centric accelerators or data-centric accelerators during the execution of the model. This significantly improves energy consumption for those 24 Google neural network models and also improve inference throughput. We are going to see more details on this work later on. Graph processing applications also can be accelerated following genomic analysis applications also can be accelerated using similar approaches, where instead of bringing the data from the storage to do, for example, a DNA sequence alignment, we do the alignment inside, or some portions of the alignment inside the storage themselves, hence allowing us to move fewer amounts of data to the hardware units for computation. I'm not going to get into details over here because we're going to have a talk dedicated to this later on. So this was a very fast pace overview of what is possible to be done in processing in memory and processing near memory architectures. We are going to see more details on all of those next during this workshop. But I just want us to be in a similar mindset where we are going to think of designing systems in a memory-centric way. So our first question is application memory bound? If this application is memory bound, by what type of computation primitive this application is memory bound? Can I move this primitive to the memory chip themselves? And if so, how? So this is what we are going to try to answer here, one step at a time. Again, we have more information on our PIM book chapter. And next, we are going to be discussing processing using memory architectures. Is there any question to what I just discussed? Question? So the work that we did before was transparent from the programmer, but we had to have some hardware inside the chip themselves to do some efficient computation, especially prefetching. So for the graph processing part, we need to, in order to have high throughput utilization, we need to enhance memory level parallelism so that we can occupy the memory chips as much as possible. One way of doing that is changing the software itself and manually exploiting that parallelism via thread, for example. But another way is to try to prefetch the next vertex that a graph needs to iterate over. And then this is what we do in this work over here. We have a hardware unit that is responsible for that. Of course, the ideal would be to have a collaborative execution from the software and the hardware, so that a programmer, for example, can annotate with metadata which portions of the data can be executed in parallel, which one not. And there are works that propose to do systems for graph processing like that for using similar architectures. Okay, so if not other question, let's move to more technical stuff. Okay, so this is my favorite subject related to processing memory. My PhD thesis was all about this. And for me, it's very fascinating to tell people about this and also to think about this type of architectures. So this is going to be very technical. So if you have any questions about the details, please feel free to stop me and ask for questions. So we are going to discuss those processing using memory architectures that I mentioned earlier that are capable of performing computation using the analog operating principles of the memory cells themselves for such computations. Forget about logic. We are not going to add logic to the memory chip themselves. Every time that I say that I'm doing X computation, there is no logic doing that. It's literally the memory itself doing the computation. And this is going to be clear when I explain how a memory chip works right now. Brief background on DRAM. We are going to be discussing mostly DRAM-based processing using memory next on. So you have your DRAM model in your laptop, for example. Your DRAM model is composed of many DRAM chips, and inside the DRAM chip, you have many DRAM banks. Inside a DRAM bank, we have what's called a DRAM subarray, which is a 2D array of DRAM cells. So those DRAM cells are horizontally connected to a word line and vertically connected to a bit line. So bit lines are connected to sense amplifier, and a collection of sense amplifier is called a row buffer. A DRAM cell itself is composed of access transistor, a storage capacitor, which store data as a voltage level, and an access transistor, which allows data to move from the storage capacitor to the bit line and eventually to the local sense amplifier. This local sense amplifier here that is not drawn here, but it's composed of two back-to-back inverters. So it's a differential sense amplifier. So you have one inverter, and the other side is connected to the input of the first inverter. So DRAM operates using three main commands: activate, a read, and a perturb. So this is the initial state of your DRAM subarray. We have one row which have many of those storage capacitors, and initially everything is precharged to half a reference voltage, which is half VDD. So in order to access the data in this storage capacitor, the memory controller first issues a activate command. So this activate command is going to raise the word line, allowing the storage capacitor to be connected to the bit line. And this is going to let the storage capacitor to lose its charge to the local bit line, generating a perturbation to the initial voltage state of the local bit line. The sense amplifier is enabled and is going to sense the difference of the perturbation voltage that is generated by the connection of the storage capacitor to the local bit line, and it's going to amplify this difference either to a logic 1 or a logic 0. So in this example here, it's going to be a logic 1. So after this amplification happens, the data is rewritten to the storage capacitor to a fully restored state. So it's going to be here a fully 1 in this example. So after this process is done, this activation process is done, the data in the local from the DRAM cell is latched in the sense amplifier. The memory controller can issue column access to portions of the data that's stored in this local sense amplifier. So once all of the column access are finished by the memory controller, and there is another request to the same DRAM bank, the memory controller issues a pre-charge command. So this basically disconnects the local word line, breaking down the path from the storage capacitor to the local sense amplifier. Pre-charge or put the local bit lines to again to the initial reference voltage, half VDD in our example, and finally disable the sense amplifier. So this is how DRAM works. So it's exactly how your DRAM chip on your laptop is working at this very moment. So you already saw this, we can use this in-DRAM row activation to perform in-DRAM primitives. So for example, if I have a source row here and I activate this source row, the row is going to be bring to the local row buffer. But instead of issuing a pre-charge or a read command to the local row here, if I send another activate to another address inside the same DRAM array, what is going to happen is that this second row, the DRAM cells are going to be connected to the local bit line. Recall this access transistor over here. So this cell is going to be connected to the local bit line, and then now I have a path between the local row buffer and the second row that I activated. However, the data that was already latched in the local row buffer before accessing the second row was the data for the first row, for row A. And the sense amplifier here is designed to have a higher drive than the capacitance of the DRAM cells themselves. So what is going to happen is that this higher drive sense amplifier is going to pull the data that was latched before from row A back to the DRAM cells from row B, hence allowing us to this in-DRAM row cop operation. So basically, by doing back-to-back in-DRAM row activations, we can do these in-DRAM row copies as without any modifications to the DRAM chip themselves. And as I mentioned, this might seem like why this is not available in my chip right now, why the manufacturers are not allowing this. I don't know, but as I'm going to see later on, this is already possible as DRAM chips in the market right now. So this is just another view of the same thing that I just mentioned over here. So I have the source row and I have the destination row. The source row stores voltage of 1. Everything's pre-charged initially. So I activate the source row. The DRAM cell is going to lose charge to the local bit line, generating a perturbation. The local sense amplifier amplifies that difference to a logic 1. Then I activate the second row, destination here. The local sense amplifier is storing the previous activated data, so 1. When the connection from the destination cell happens, the data that was stored in the local sense amplifier is going to be pushed back to the destination row, hence allowing for the in-DRAM row copy. Is there any question how this is happening? Okay, if not, you might ask, okay, all of this can be done, but the data needs to be in the same array, the same subarray. You can do in-DRAM row copy operations for data across different DRAM buses by using this share interconnect that is already available inside the DRAM chip themselves. So the idea here is the same. You do the activation, and then you pipeline the data cache line by cache line via this share data bus inside the DRAM chip themselves. This is not as efficient as doing the computation inside the single DRAM subarray, but still it provides higher latency, lower latency and lower energy than moving the data to the CPU. So this is just the generalization of what I just mentioned. This process that I mentioned for in DRAM row copy across different banks. It's called pipeline serial mode because you're pipelining the data across the narrow channel inside the DRAM chip themselves. And all of this can be done with very negligible area cost. So if you we use row column and compare it to DMA-based engine, you already saw this graph. We can have orders of magnitude improvement in latency and also energy compared to moving the data to the CPU. So, okay, this is very nice. We can do this in DRAM row copy operations by doing this back-to-back in DRAM row activations. So let's do something more interesting. This is just to move data inside the different DRAM subarrays inside the DRAM bank. So if you want to move data inside across different DRAM subarrays inside the DRAM bank, the problem is that there is no interconnect that connects the adjacent DRAM subarrays inside the DRAM bank itself. And for us to do so, we need to have some isolation transistors that connects neighboring DRAM subarrays and allow us to do the same operation that I just mentioned, is back-to-back in DRAM row copies across different rows, across different DRAM subarrays at high performance. This is called LISA. Okay, so we start very simple with this in DRAM row copy operation. Let's look at the triple row activation. So now that you know how activation operates, hopefully this slide that you already saw makes more sense. So if I activate 3 DRAM rows at the same time, the 3 DRAM cells are going to simultaneously perturbate the local bit line. So here the perturbation is going to be upwards because the data is stored in the DRAM cells here the DRAM cells have charged data. So since this perturbation is going to be upwards, the local simplifier is going to pull these activations to a logic 1, and the data is written back to the DRAM cells, hence realizing in DRAM majority of 3 operation. Again, you can control that by setting one of the rows to either 1 or to 0. So the main question here is for us to be logic complete. Okay, we have AND and OR, but this is not logic complete, right? We still need a NOT. So if you have a NOT, we can have NAND, and if you have NAND, you're Boolean complete. You can do whatever you want inside the DRAM chip. The thing is that there is already a NOT gate inside a DRAM chip, as it is right now. As I mentioned before, the local simplifier is actually composed of 2 back-to-back inverters connected in a loop. So we can just take the output of one of those inverters and route it back to the DRAM cell. So now we can do in DRAM NOT operation. So how this is working, right? So I'm going to guide you to the circuit very quickly. So we have here the original DRAM cell, and then we have the access transistor, and then we have one side of the local simplifier. If I activate this row here, this transistor is going to be enabled. The data is going to flow from this cell down to this simplifier over here. Since this is a NOT gate by definition, the data, if the data was 1, this is going to be in the end over here of this NOT gate is going to be 0. And then we have this new access transistor here, which we are going to enable as well. It is going to create a path from this NOT gate back to the DRAM cell. So now I have the store here. Initially, I have 1. If I enable this transistor over here, what we are going to have is going to be 0, so coming from the end of the other end of the sense amplifier. So by doing so, now we can do in DRAM row copy. We can do in DRAM majority of operations and the NOR operations, and I can also do NOT. So, and if I can do all of this, I have a functionally complete compute chip. I don't need anything anymore. This is again another view of what I just mentioned before of moving the data back with the NOT operation. So doing this operation, we can significantly implement book bitwise operations inside the DRAM chip, like NOT, AND, NAND, OR, XOR. And using those operations, we can accelerate several applications that require such book bitwise primitives, like database operations. So this is just one example here of a bitmap index that can be accelerated using such in DRAM bitwise primitives. The way that this works is by for example, if I have a query, I create a bitmap index for each one of the queries in my database. So people from the age of 18, from 18 to 25, and then I end basically the database which the bitmap index that I generate. So if I do computation like that, I can significantly improve the bitmap index in the system compared to using a baseline CPU, because I'm not moving any data out of my DRAM chip themselves. We can also accelerate other type of database applications like bit waving. So if you want to have a query, for example, count the number count for this database T, all of the variables that are between a range. I can translate these again to a sequence of AND and OR operations, and I can accelerate that using this triple row activation that I mentioned before, and significantly improve performance as well. So this was Mbed. Is there any question related to how this is being done? Question? So all of those operations are being performed at the granularity of a DRAM row, because that sense amplifier secretly is shared across all of the DRAM cells in a row. And in DDR4, in a DRAM rank, we have 65,000 columns. So when you do ends, you are ending 65,000 elements at once. Of course, this depends on the technology that you are using. For example, low power DDR4 usually have smaller row sizes, but it is still in the orders of the thousands. So it's very large. Okay, so that was Mbed and row clone. So now we can do in DRAM row copy with row clone. We can do in DRAM AND and OR and NOT operations. So the question now is, how can I generalize those operations to do more complex things like addition and subtraction? So if I give you a logic synthesis library, right, with NAND gates, if you took a digital design class, you know that with that you can do a RIP carry header, for example, right? And this is exactly what we are going to do over here. We are going to use those primitives to perform more complex operations over the many columns inside the DRAM row. So basically, we are going to use two main ideas. So the main problem of doing that in DRAM using those logic primitives is that if you want to do a RIP carry header, eventually you need to propagate a carry, right? So bit 0 generate a carry to bit 1, and bit 1 to bit 2, so on and so forth. But there is no connection across the different DRAM columns inside the DRAM subarray. So let's think about this as a DRAM subarray. There is no way for me to move data from this column here to this column here without adding interconnect, because the DRAM chips are not designed to move data vertically across different columns. So instead of adding this interconnect, which is very high cost, we are going to transpose the data. So instead of storing the data, you can just shift your heads. So basically, the yellow, if you have a 4-bit data element, right? The way that is storing your DRAM chip is each bit is going to be stored in a single DRAM column. So this yellow here will be one column, the other one in another one, so on and so forth. So instead of doing that, we are going to store all of those bits in the same column. So all of the yellows here are in the same column, spanning different DRAM rows. So this is this is the most significant bit. This is bit 0, bit 1, bit 2, bit 3. And then if I have another elements, like if I have an array with 4 elements, each one of those elements in the array are going to be spanning one of those DRAM columns inside the DRAM subarray in a vertical data format. So what does it allow me to do? Now it allows me to move data across different rows. I don't need to move data across columns. I can move vertically across different rows using that in DRAM row copy that I mentioned earlier. So if I need to generate a RIP carry header now, and this bit here, bit 0, generated a query to bit 1, the data is already stored in the same DRAM column. I just need to copy using that primitive that I mentioned earlier, this first row here to the second row. So basically, this allows us to do implicit bit shifting operation because again, the data is in the same column, and allows us to have this execution model where I have different, I can see this substrate as a SIMD substrate, a single instruction multiple data. We have where each one of those columns inside the DRAM chip, so those 65,000 columns are going to be SIMD lanes. And I'm going to execute the same computation over all of those SIMD lanes at once in a bulk manner. So the second thing that we are going to use is majority-based logic. So what I mentioned earlier in Ambit was all based on AND and OR and not gates, right? But what I have in the ends when I do a triple activation of inside the DRAM chip is a majority gate, because what I have in the sense amplifier is a differential circuit. So by leveraging majority logic instead of leveraging AND and OR NOT-based computation, I can reduce the number of individual row activations required to do a single operation, improving performance and throughput as well. You're going to see how this is going to translate to performance later on. So based on these ideas, we propose this SIMDRAM framework. So basically, this framework is a three-step framework that takes a required arithmetic operation, let's say a RIP carry adder, and generates the required sequence of INDRAM operations, INDRAM row couples and INDRAM majority operations, in order to generate that INDRAM, initial RIP carry adder inside the DRAM chip themselves. Again, I'm not adding this logic for this RIP carry adder in the DRAM chip itself. It's all based on activations. So let's see how this works. So the first step basically converts the input logic representation that you want, like a RIP carry adder using Boolean logic, to a naive majority-based version of the same graph. And this can be done quite easily because there is this equivalence between AND gates and OR gates. So an AND gate is equivalent to a majority gate if one of the inputs is 0, and OR gate is equivalent to a majority gate if one of the inputs is 1. So basically, I take my initial RIP carry adder here, I go to each one of the gates, and I replace them using this equality to majority gates. Now I have the same implementation of the circuit that it only uses majority and not gates. But still, this is not necessarily the most efficient implementation. So by applying optimization logic on top of the circuit, think here like when you're minimizing a Boolean circuit, like using the Morgan law, for example. We can reduce the number of majority gates that is in the circuit to, in this example here, only 1. This is going to translate to higher performance because each one of those majority gates here are going to later on translate into an INDRAM row copy or INDRAM majority of 3 row activation. So if I have fewer row activations, the higher the performance for my system. So in the second step, we are going to generate what's called a microprogram, which is basically a recipe that tells the DRAM chip which rows to activate at each given moment in time to realize the target INDRAM row activation that you want, the INDRAM arithmetic operation that you want to execute. And this step is going to be broken down into 2 tasks. Task 1, which we're going to allocate DRAM row to operands, and task 2, which you're going to generate the microprogram. So I start with the first task. So we have some constraints if you want to do this design in DRAM. The first constraint is that you have limited number of rows for compute, and also we have this destructive behavior. I don't know if that was clear, but every time that I do a triple row activation in the DRAM involving 3 DRAM cells, the output of the triple row activation is stored at the 3 DRAM rows that I activated at once. So I lose the data. So if I need that data back, I need to copy it to a temporary space. So based on that, we generate this allocation algorithm that basically first maps the inputs of the majority gates to rows inside the DRAM chip. And after that, issues the triple row activations that generates the required computation. The final step is to, after generating this recipe that tells me how to execute that INDRAM row activation, INDRAM arithmetic operation inside the DRAM chip, we need to optimize that to reduce the number of row activations, so improve performance. and also generalize the computation, because this sequence of operation here performs the majority operation here for 1 bit. So if you have many bits inside of your data word, we need to repeat this computation as many bits as possible. So basically what we are generating here is a bit serial SIMD engine inside the DRAM chip itself. So this final recipe that tells my DRAM chip how to execute that DRAM addition operation is stored in DRAM for future use, and also in a CPU ISA for the programmer to instantiate. So finally, we have a control unit in the memory controller that automatically dispatch those operations to the DRAM chip themselves when it encounters a new DRAM primitive. So I mentioned earlier that for all of this to work, we need to store data in a different data format, right? So we're not storing data in the conventional horizontal data format. We need to transpose the data to this vertical data format, where the different bits of a data word span different rows inside a single DRAM column. To do that efficiently in this work, we implement a transpositional unit that sits between the last level cache and the memory controller, which automatically transpose cache lines belonging to memory objects that are going to be executed in DRAM efficiently. So this have low impact on the throughput of the operations, at the same time that incurs low area cost. So we use this framework to accelerate, to implement 16 different DRAM operations. So addition, subtraction, division, multiplication, ReLU, predicative operations, min-max, all of those. And we compare its throughput to a CPU, GPU, and embedded, depending on the number of DRAM banks that you use for computation. So the more DRAM banks that you enable for computation, the more columns you have, the more SIMD lanes, and the more performant your system are going to be. So compared to the CPU, GPU, and embed, SIMD-RAM, which is the name of the mechanism, significantly improves throughput for those 16 different operations, and also significantly improves energy efficiency as well, in the orders of 2 orders of magnitude compared to the CPU. Then we use those new DRAM arithmetic operations to accelerate 7 real-world applications, including databases and machine learning applications. And we see significantly improvement compared to the CPU, GPU, and also prior process using the RAM system. So in conclusion, SIMD-RAM enables us to compose those DRAM arithmetic operations using that primitive that I mentioned earlier, that DRAM row copy, and that DRAM majority of 3 and not operations into more complex primitives. And in the paper, we have more analysis on how to handle system integration challenges. So it's a lecture on SIMD-RAM, which I'm going to skip. So all of this is very nice. We can do DRAM row copy, DRAM majority, and also DRAM arithmetic operations in DRAM chip. But is this all of that is done? So what if my computation? What if the granularity of my computation does not match the granularity of my DRAM chip? What is going to happen? How can I fix the high latency of bit serial operation? All of this is going to be answered in the follow-up work that I'm going to talk next. But I guess this concludes that first part of processing using DRAM. Is there any question what I just mentioned? Okay, if not, we are going to have one of the invited talks right now, and which you are going to see how this type of computation can be done in commodity off-the-shelf DRAM chips as they are today. Let's just check if Ismail is online. It's not yet, right? Oh, maybe I want too fast. Yeah, we can take the coffee break, and then when we return, he should be here. So let's take the 20 minutes coffee break, and then when we return, you're going to have the invited talk. Thank you very much. Oh, he joined. Ismail, feel free to share your screen.
Sure.
Can I spotlight you?
Okay.
PIM.
Do you see the slides?
Yes, let me just quickly announce you.
Sure.
Okay, welcome back, everyone. Hope you had a good coffee break. Unfortunately, I didn't find any chocolate chip cookies. Now you're going to have an invited talk from Ismail. Ismail is a second-year PhD student in the Safari Research Group, and he's been conducting a lot of research on real commodity off-the-shelf DRAM chips and seeing how we can actually perform those primitives that I just mentioned before in a modified DRAM DRAM chips. So Ismail is going to show some of the results for such works. If you have any question, please let me know. I'm going to pass the microphone around. So thank you very much for joining, Ismail, and feel free to take this stage.
Okay. Thanks a lot for the introduction, Geraldo. Hello, everyone. I'm Ismail. Today, I'll be presenting my works on, as Geraldo said, on modified DRAM chips and its capability. I'll be mainly focusing on the work that we did for HPC 2024 called Functionally Complete Boolean Logic in Real DRAM Chips. So without further ado, let's get started. Okay, let's start with an executive summary. As you, I think, know now, processing using DRAMs can alleviate the performance and energy bottlenecks caused by the frequent data movement between main memory and processing units. And prior work showed that existing DRAM chips, unmodified DRAM chips, can perform 3-input majority and 2-input AND and OR operations in real DRAM chips. However, these proof of concept demonstrations on real DRAM chips do not provide functionally complete operations or not operation and 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 OR operations with more than 2 inputs. So they are limited to 2-input AND and OR operation, majority tree operation, and that's it. In this study, we tested a total of 256 DDR4 chips from 2 major manufacturers, and we observed that off-the-shelf DRAM chips can perform NOT and 2, 4, 8, and 16 input AND, NAND, OR and NOR operations with very high reliability, more than 94% success rate, which is a reliability metric that we introduced. I'll give more detail later. And data pattern and temperature only slightly affect the reliability of such operations, less than 2% decrease in the reliability metric that we use. So here's the outline of my talk. I'll give a brief background, but let's say I'll refresh your minds. So you know already the data moment bottleneck, because today's computing systems are processor-centric and all data processed in a processor at a great system cost. As a result of this, more than 60% of the total energy spent on data movement. And processing in memory is a promising paradigm to alleviate such data movement bottlenecks. And there are 2 main approaches for that. First, processing near memory, and second, processing using memory, where we focus on our work that uses the analog operational principles of memory cells to perform computation. In our context, we'll use DRAM, which is processing using DRAM paradigm. So DRAM is used as memory in many computing systems, and the DRAM module consists of multiple DRAM chips. Each chip contains multiple DRAM banks, and each bank composed of multiple subarrays and sense amplifiers. And within each subarray, there's a 2-dimensional array of DRAM cells. These cells are organized into rows that are selected using word lines, and the cells that are connected to a row of sense amplifiers via bit lines. And today's DRAMs, to achieve high-density chips, Open bitline architecture is widely adopted in modern DRAM modules. In this architecture, each subarray's bit lines are connected to 2 rows of sense amplifier, one above and one below the subarray. This results in neighboring subarrays share a common component called sense amplifiers. And during an activation, another bit line in a neighboring subarray is also involved to serve as the reference of the sense amplifier, which is a bitline bar in this example. After a successful activation, the bitline and bitline bar have a complementary voltage. This is because of the sense amplifier is actually consists of 2 back-to-back inverters, which is essentially a NOT gate. And let's take a look at the major DRAM operations that we focus on in this study. So to access data, memory controller first needs to send an activate command to a row that contains the data and fetch rows content into the sense amplifiers. And then column accesses are serviced from these sense amplifiers. And finally, the subarray or bank needs to be precharged to get ready for the next activate command to activate another DRAM row. And our goal in the study is to understand the capability of real DRAM chips beyond just storing data and rigorously characterize the reliability of this capability. To this end, in this study, we experimentally demonstrate that real DRAM chips can simultaneously activate up to 48 DRAM rows in 2 neighboring subarrays, can perform NOT operation with up to 32 output operands, and can perform up to 16 input AND, NAND, OR and NOR operations. And to be able to test and characterize this, we use an FPGA-based DDR4 testing infrastructure developed from DRAM vendor that enables fine-grained control over DRAM timings and temperature. We test a total of 256 DDR4 chips from 2 major manufacturers, and we cover different die divisions and chip densities, which is essentially different DRAM architectures. And in this study, we focus on 2 neighboring subarrays, here denoted as subarray X and subarray Y, which share a common component, sense amplifiers. And we perform our experiment using the following command sequence: activate row A, precharge, and activate row B, where row A is in subarray X and row B is in subarray Y. We carefully sweep row addresses, row A and row B, and the timing parameters between each command in this command sequence. And now let's move to our first characterization, which is simultaneously activating 48 rows in 2 neighboring subarrays. Our key observation is that activating 2 rows in quick succession can simultaneously activate multiple rows in neighboring subarrays. So here you remember this pictorial example, we have subarray X and subarray Y, and they share a sense amplifier. When we issue activate row A, precharge, and activate row B, while respecting the timing parameter without violating any timing parameter, we will activate only a single row at a time. First, we will activate row A, and then we will precharge it, we will close it, and then we will activate row B. And at a given time, only one of them will be activated. However, if we greatly violate these timing parameters, we observe that we can activate multiple rows at once, simultaneously, in neighboring subarrays. To rigorously characterize and understand which and how many rows are activated, we sweep 2 key parameters, row A addresses and row B addresses, to cover all rows in these 2 neighboring subarrays. We observe that off-the-shelf DRAM chips have 2 distinct sets of activation patterns in neighboring subarrays when 2 rows are activated with violated timings. The first one is exactly the same number of rows are activated in each subarray. We observe that we can activate up to 16 rows in each subarray, a total of 32 rows. And the second pattern is twice as many rows in one subarray are activated compared to its neighbor subarray. We observe that we can activate up to 16 rows in one subarray while activating 32 rows in its neighbor subarray, a total of 48 DRAM rows. From this experiment, our key takeaway is off-the-shelf DRAM chips can simultaneously activate up to 48 rows in 2 neighboring subarrays. And for more detail, more hypothesis results, I would like you to refer to our paper. And then now our second analysis, the NOT operation. We will see how this multiple row activation will help us to realize a NOT operation in real DRAM chips. The key idea is to leverage the connection between two neighboring subarrays, the NOT gate and the sense amplifier. By simultaneously activating rows in neighboring subarrays, we can connect these rows through a NOT gate. As an example, source and destination rows in neighboring subarrays. And if we first activate the source and then activate the destination without deactivating the source, this results in sense amplifier to drive the negated source value to the destination, which is negated A in this example. And let's see how we can perform NOT operation in real DRAM chips at a lower abstraction level. As an example, we have source and destination cells, both store ground, and bit lines are precharged to VDD over 2. We first issue activate command to source, which asserts the source word line, and then starts charge sharing process between source and its bit loop. And then we wait for nominal timing parameters, which assures sense amplifier that amplifies the voltage difference and drives ground to the source bit line and drives VDD to destination's bit line because of the NOT gate and the sense amplifier. And then we issue back-to-back precharge and activate command with violated timing parameters. This operation leads to connecting destination cells to its bit line, keeping the sense amplifier enabled and keeping the destination's bit line to VDD. Eventually, as sense amplifier is enabled and bit line is still VDD, the negated value of the source, which is VDD, is written to destination. So to characterize this capability, similar to our previous analysis, we sweep row addresses where row A and row B to cover all rows in neighboring subarrays, and we sweep DRAM chip temperature from 50 degrees Celsius to 95 degrees Celsius. To evaluate the reliability of this NOT operation, we define a metric called success rate. Success rate for a DRAM cell refers to the percentage of correct trials of a tested operation stored in the cell. We test a total of 10,000 trials and record the success rate for each tested cell. Here, for example, we have 4 trials and 2 of them are correct and 2 of them are incorrect. For this specific cell, the success rate is 50%. And this analysis provides 2 key takeaway lessons. First, off-the-shelf DRAM chips can perform NOT operations with up to 32 destination rows. Second, temperature has a small effect on the reliability of NOT operations. Now let's take a look at our first result. In the x-axis, you'll see the number of destination rows. And in the y-axis, you see the success rate distributions across tested DRAM cells. We observe that there is at least one DRAM cell that can perform the NOT operation with 100% success rate. And we conclude that off-the-shelf DRAM chips can perform NOT operations with up to 32 destination rows. And our next experiment is the impact of temperature on the reliability of NOT operation. To maintain a reasonable experiment time, we use destination cells that can perform NOT operation with more than 90% success rate at nominal temperature, which is 50 degrees Celsius. In this plot, you'll see x-axis is the same, number of destination rows, and the y-axis is again the same, the success rate distribution, and each colored box, hue, represents a different temperature level, from 50 degrees Celsius to 95 degrees Celsius. And we observe that from 50 degrees Celsius to 95 degrees Celsius, there is only 0.2% variation in average success rate. Our key takeaway from this experiment is temperature has a small effect on the reliability of NOT operations. And then now let's move to our last analysis, which is AND, NAND, OR, and NOR operations. Until now, we demonstrated that off-the-shelf DRAM chips are capable of activating multiple rows and performing NOT operation. Now we will see how these 2 demonstrations enables us to perform up to 16 input AND, NAND, OR, and NOR operations. The key idea is to manipulate the bit line voltage to express a wide variety of functions using multiple row activation neighboring subarrays. So let me give you the key idea by showing 4 cells, X, Y, A and B, 2 from each neighboring subarrays. Now, if we activate these 4 cells simultaneously, the bit line at the bottom subarray becomes the function of voltages in X and Y. And the bit line at the top subarray becomes the function of the voltages in A and B, which is essentially the average of A and B for top subarray and the average of X and Y for the bottom subarray. And sense amplifier will compare the voltages at the bottom bit line to the voltage at the top bit line and figure out which one is high. Now let me show you the basic intuition to perform 2-input AND and NAND operation. For this example, we have 2 subarrays, reference and compute subarray, each of which consists of 2 cells. Reference subarray cells store VDD and VDD over 2. As a side note, we store VDD over 2 using frac DRAM's technique, a prior work. And in the compute subarray, we have X and Y. With this setup, if we activate all these 4 cells using act-per-act sequence, we will get AND of X and Y in the compute subarray and NAND of X and Y in the reference subarray. To simplify things, assume bit lines will have the average value of their corresponding cells' voltage values, such as reference bit line will be the average of VDD and VDD over 2. Now, let me prove that that is the case. I'm going to cover all the combination of the X and Y values, starting with where both of them are 0. So now when X and Y is 0, their cell stores ground. When we perform act per act, we see that reference bit line becomes 3 VDD over 4, which is the average of VDD and VDD over 2. And the average of ground and ground is basically a ground. Then sense amplifier will compare the voltages on the bit lines. Since 3 VDD over 4 is higher than ground, reference cells in the reference subarray will store VDD, while cells in the compute subarray will store ground, which we can represent like this in the truth table. And now on to the next one, where X is 0 and Y is 1. As again, the bit line voltage still lower than 3 VDD over 4, right? X is 0 and Y is 1, the average is VDD over 2. Sense amplifier will compare the voltages again, and since reference bit line is still higher, reference cells will store 1, while compute cells will store 0. And for the third one, it's the same. Still, we have VDD over 2 because of X store VDD, Y store ground, the average is VDD over 2. When sense amplifier compares these 2 voltage values, still reference subarray has higher voltages, thus its cells will have VDD and compute cells will have 0. For the fourth one, for the last row of the truth table, where X and Y both are VDD, this results in compute subarray to be VDD and the reference bit line is 3 VDD over 4. Again, sense amplifier will amplify the voltage difference. However, this time, compute subarray's bit line is greater than reference subarray's bit line. As a result, reference subarray will store ground and compute subarray will store VDD. Consequently, this example shows how compute subarray stores the result of X and Y, and the reference subarray store the result of the NAND operation of X and Y. Here, as you can see, now compute subarrays has X and Y, AND operation of X and Y, and the reference subarray has NAND operation of X and Y. By carefully choosing the voltage levels of the cells in the reference subarray, we can express many input AND, NAND, OR, and NOR operations. I would like to again refer you to our paper for more analysis. Now I just demonstrated the 2-bit AND and NAND operation, but in the paper we describe how we can perform 2-bit OR and NOR, and also we generalize it to N-bit, N-input AND, NAND, OR, and NOR operations. So our characterization methodology is the same as before. We sweep row A and row B addresses to cover all the rows in the neighboring subarrays. And we have 3 key takeaways from this analysis. First, off-the-shelf DRAM chips can perform 2, 4, 8, and 16 input AND, NAND, OR, and NOR operations. And they can perform AND and OR and NOR operations with very high reliability, and data pattern slightly affect the reliability of AND, NAND, OR and NOR operations. Let's see the first result for this analysis. In this plot, x-axis represents the number of input operands, and y-axis shows the success rate distribution across DRAM cells. And the hue shows the type of the operation, AND, NAND, OR and NOR. Our key takeaway from this experiment is that off-the-shelf DRAM chips can perform 2, 4, 8, and 16 input AND, NAND, OR and NOR operations. And 16 input AND, NAND, OR and NOR operations has very high success rate, more than 94% on average. And our second analysis is the impact of data pattern. This plot depicts the effect of data pattern on the NOR operation success rate. X-axis shows X and Y-axis show the same thing, and hue shows the tested data patterns. Either we write all ones or zeros in a row or random data. We observe that there's only less than 2% variation in average success rate across all number of input operands. And this trend is consistent across all tested operations. Basically, data pattern slightly affect the reliability of AND, NAND, OR and NOR operations. In the paper, we have a lot more things that we cover. For example, detailed hypothesis and key ideas to perform NOT operation, many input AND, NAND, OR and NOR operations. How the reliability of bitwise operations are affected by the location of the activated rows, temperature for and then OR and NOR operations, DRAM speed rate, chip density, and die revision. And also we discuss the limitations that we faced while we were testing off-the-shelf DRAM chips. Our paper, the extant version, is available on arXiv, and also we open sourced our code base on GitHub. You can find it in our Safari GitHub repo. And let me conclude my talk for this paper. The experiment demonstrate that off-the-shelf DRAM chips can perform functionally complete Boolean operations, many input up to 16 input AND, NAND, OR and NOR operations, and we characterize the success rate of these operations using 256 DDR4 chips, and we observe that we can perform NOT and 2, 4, 8, and 16 input AND, NAND, OR and NOR operations with very high success rates. Data pattern and temperature only slightly affect the reliability of such operations. And we believe these empirical results of this paper demonstrate the promising potential of using DRAM as a computation substrate. And that was it for this paper. Maybe I can get the questions after I quickly cover the other paper, if that's fine. What do you think, Geraldo?
Hi, Ismail. Yes, that sounds good.
Okay, cool. Thanks. So second paper is simultaneous binary activation in off-the-shelf DRAM chips. Here I'll just summarize things and give you the key idea behind just one new functionalities that we uncovered. So this paper is published in DSN 2024 last year. Let's start with an executive summary. So still the same motivation, PUT can alleviate the data movement bottlenecks, and off-the-shelf DRAM chip can perform 3-input majority and in-DRAM copy operations. And our goal is to experiment, analyze, and understand the computational capability beyond that of prior works, and the robustness of such capability under various operating conditions. And to this end, we test a total of 120 DDR4 chips from 2 major manufacturers. And we observed that off-the-shelf DRAM chips can perform not just MASH3, but MASH5, MASH7, and MASH9 operations, and not just copy one row to another, but can copy one row to up to 31 different rows at once. And we observed that storing multiple redundant copies of majority's input operands, which we call input replication, drastically increases robustness. One example for that one, the prior works were using 4 rows to perform majority 3 operations. Now we use, for example, 32 rows to perform majority 3 operations by replicating each input data 10 times, which help us to increase the robustness of such operations. And lastly, we observed that operating conditions in this paper, we test different temperature levels, different voltage levels and data patterns, and also timing parameters affect the robustness of DRAM operations by up to 12% success rate. And our paper is, again, available on GitHub, the code base, and you can just directly test it. So to summarize the paper, we leverage the simultaneous many row activation, and we observe that we can perform majority of X, where X is greater than 3. We can increase the robustness of majority X operations, and we can copy one row's content to multiple rows. Let me cover the last part of the paper, which is copying one row's content to multiple rows. The key idea is, since we can activate many rows simultaneously, we can copy one row's content to other simultaneously activated rows. Let's recall row clone example where we copy source to destination. In row clone, we first activate the source row, which will copy its content to sense amplifiers, and then we activate destination row to drive the sense amplifiers content to destination rows. In our mechanism, which we call multi-row copy, we have several destination rows. Here we activate many destination rows simultaneously, and thus sense amplifier drives its content to these destination rows. And we characterize the robustness of such capability. And in this in this plot, we have y-axis shows the success rate, the same success rate that we used in the prior paper, and the x-axis shows the number of destination rows, number of rows that we copy the source row's content, from 1 to 31 rows. And we plot the success rate distribution as a box and whiskers plot. And we observe that the average success rate across all tested number of destination rows is actually higher than 99.98%. And we conclude that DRAM chips can copy one row's content to up to 31 rows very reliably, almost 100%, but unfortunately it's not 100. Very close. And our extended version is available on arXiv, and our work is fully artifact evaluated and got every patches. And you can download our code from GitHub and start testing right away. And that was for this, a very quick run for this paper. And if you would like to check, if you're interested, there's a QR code for the paper and GitHub repo. Yeah, I'm happy to answer your questions if you have any.
Okay, I have one question. So all of this is very nice, but we talked recently here in the workshop about read disturbance, and if you access many DRAM rows at the same time, you might end up generating Rohammer bit flips. So does this type of real in DRAM operations exacerbate Rohammer?
Now I can answer this question. Definitely, yes. We have an upcoming paper on ISCA actually in probably 10 days, which we test again like 40 DRAM modules, more than 300 chips. And we perform this multiple row activations, this many row activations, and check how they affect, like whether they increase the read disturbance vulnerability. And we unfortunately saw that it's affecting a lot. Now we we see that like the lowest that you need to get a bit flip is now actually 150x lower than your best known Rohammer data access pattern.
So do you think this is good news for memory-centric computing or bad news, or good news for researchers?
I think good news for researchers. So for the future, probably we will need to take this into account so that the read disturbance vulnerability while we design these chips. So maybe a side note, these chips are not designed to perform such operations, right? They just design to store some data. While they designing, hopefully, they will design, put enabled chips in the future. They'll need to take this into account, unfortunately.
Okay, thank you very much, Ismail. So if you are interested on processing using DRAM and Rowhammer and you're attending ISCA, when is your session, do you know?
June 24th, I guess, session 5A in ISCA.
Perfect. Attend session 5A in Tokyo and talk to Ismail.
Yeah.
So is there any other question? Okay, if not, thank you very much, Ismail, for joining so late. He's in Zurich, it's very late in time, but thank you very much for the great talk.
Yeah, thanks a lot for the opportunity, Geraldo.
Okay, Lo, let's get back for lunch. Okay, is it all right? Okay, perfect. So that was just a highlight to say that everything that you are mentioning before on those processing using DRAM, on operating DRAM chips in a very different way that they are designed to operate. It's not only daydreams of academics, it's actually what we can do on real chips if you violate some time parameters. So hopefully DRAM manufacturers are going to catch up very soon, and then you're going to see those operations being supported more efficiently in current systems. So going back to what we talked before the coffee break, we were in a succession of complexity of in-DRAM operations. We start very easy with in-DRAM row copy and in-DRAM bitwise operations with what is I mentioned and what Ismail discussed, and also simple in-DRAM arithmetic operations, right, with SIM-DRAM. So we are going to follow up next with MIMDRAM. So what I mentioned before was that we can do this book bitwise arithmetic operations in DRAM chips, but they operate at a very large access granularity. There was a question here, and then I discussed that there are many DRAM columns inside the DRAM models, around 65,000 for the DDR4 rank. And when you are doing those book bitwise operations, you're operating over all of those 65,000 columns at the same time. So is it efficient for real applications? So the answer is no. So no, it's not very often that you write a loop in your application that your loop is going to operate over 65,000 elements every given moment in time. And it's not only this, you might have a loop that is very large, but you need to be exact multiples of those 65,000 elements. Otherwise, you're going to end up having some SIMD underutilization of your processing using DRAM substrate. And our whole story coming from here was that we don't want to waste energy. And if you don't want to waste energy when you're doing an activation in DRAM, which is a very costly operation, or if you do that over values that are not contributing to the computation, you're going to end up wasting throughput and energy. Also, I don't know if it was clear for the examples that we mentioned before, but every time that you're doing a book bitwise operation, addition or subtraction, and or, you always have two arrays that they are operating at the same time and generating a third array. What if I want to do a scalar operation, a reduction, for example, over this array? Since what I mentioned earlier, there is no direct column communication across different DRAM colors inside the DRAM map, we are basically limited to the computation that we can do to what are called in-DRAM map operations. So we have two arrays generating a third array. At the same time, how do I program those chips? I didn't mention this before. So one, I'm saying that we can do this, we can do that, but exactly how can I translate my C codes down to these operations? So we are going to try to answer those in this work. So the first thing that we decided to do was that we want to understand how bad the SIM utilization problem is when you are trying to accelerate real applications using such commodity such in-DRAM operations. So we took many applications and we calculate what's called, or what we define as, the maximum vectorization factor. So basically, how many scalar operands can I fit into a SIM register, which is going to be used later on for computation. So ideally, you want to fit as many scalar operands as DRAM columns that you have in a DRAM model. So around 65,000 operands per SIM register in DRAM. So we took 12 applications for for 4 different benchmark suites, and we quantify the maximum vectorization factor across loops in these applications. So here, as a reference, anything above this red line that I have in this plot is going to be high utilization, so it's good. We can have high SIM utilization for your substrate, and everything that is below is low utilization. You are going to end up in throughput waste. So we make 2 observations. So the first one, we have here the distribution of the vectorization factors for each one of those applications. We see that the SIM parallelism in real applications significantly varies, not only within a given application, but also across the different applications that we analyze. And the second observation that we make is that only a small fraction of the applications that can be accelerated using processing using DRAM substrates have large enough SIM parallelism to fully exploit the processing using DRAM substrates. So basically, we did all of this work to do these nice computations, but in the end, it's not that useful if you're actually trying to accelerate real world applications. So let's try to see later on how you can make this more useful. The second problem is this reduction problem that I mentioned earlier, right? So since there is no direct communication across DRAM columns inside the DRAM subarray, we are limited to in-DRAM map operations. So I cannot reduce a vector into a scalar operation. And if you try to create a circuit that connects the different DRAM columns in the DRAM model, you're going to have very high area cost on top of a DRAM subarray. So it's not very efficient. So the third problem is programming this application. So as I mentioned in the SIM-DRAM talk, we have these new CPU ISA instructions that triggers in-DRAM row activation. So in-DRAM row copies or in-DRAM subtraction or multiplications. But who are responsible to instantiating these assembly-like operations? Is you, the programmer. So if I want to implement this simple predicated addition or subtraction operation here in C, into my process using DRAM substrate, I need to do many things. I need to map and align the input operands, those input arrays, to be in the same DRAM bank and DRAM subarray. I also need to identify array boundaries so I don't go over the DRAM subarrays. I need to maply unroll this loop to exploit SIMD level parallelism, and also map the C constructs into processing using DRAM instructions. At the same time, if there is a condition, for example, I need to manually orchestrate data movement to satisfy that predicated execution over here. But in the and this is how the code looks like after you write the assembly-like code. But in the end, you as a programmer just wanted to write a very simple predicated execution, a predication addition and subtraction execution. So it's very costly to program this type of system. So to summarize, the problem that we are trying to overcome here is that processing using DRAM large and rigid access granularity limits the applicability and efficiency for different processing using DRAM-friendly applications. And our goal in this work was to design a flexible process using DRAM substrate that overcomes these 3 challenges. So to this end, we are going to use an old idea called fine-grained DRAM access. So when you are accessing, this is nothing related to processing in memory. So anyway, accessing a DRAM chip, as I mentioned in the background, you bring the entire DRAM row worth of data to the local sense amplifiers. Even if a follow-up read or write request is going to only access portions of a DRAM row, which generates energy inefficiency. This happens because there is a signal, a global word line signal, that propagates across the different DRAM mats in a single DRAM subarray, doing an in-DRAM row activation. So prior works have proposed this idea of fine-grained DRAM, which alleviates this energy inefficiency by segmenting the global word line, allowing one to access individual portions of a DRAM mat inside a DRAM subarray. So many of those works have done this for high-efficient processing, high-efficient DRAM access, including some work from Safari and some works from people here in the audience. But now we are going to use this idea for processing using DRAM computation, this idea of fine-grained DRAM activation. So fine-grained DRAM activation for processing using DRAM provides three main benefits. So the first one, we can improve SIM utilization by accessing only the DRAM mats that have the target input data for the following processing using DRAM organization, hence minimizing the throughput loss for processing using DRAM execution. And this provides a second opportunity because now we have unused portions of a DRAM mats inside a DRAM subarray. And if we have, and we can identify independent processing using DRAM instructions, we can execute those instructions simultaneously in a multiple instruction, multiple data execution model. So the second benefit that this provides is that we can do simple modifications to the global simplify access periphery logic to move data across different DRAM mats inside the DRAM subarray, allowing us to implement in DRAM vector reduction natively. Third, there is this nice feature of DRAM mats that they have around the same number of DRAM rows and columns as the number of SIMD lanes in current vector ISA instructions. So there are around 512 rows and columns. This number might vary depending on the DRAM organization that you use, but on the is around that number. Number of columns has SIMD lanes inside the DRAM mats. And for example, in AVX 512 instructions, which also have 512 different lanes, 512 different lanes, we can use such instructions to map computation down to the DRAM mats transparently from the user. So based on these ideas, we propose MIMDRAM, which is a hardware software co-design process using DRAM system that enables fine-grained process use DRAM computation at low cost and program effort. So MIMDRAM is composed of hardware and software structures, which I'm going to illustrate next. So first, in the hardware side, we propose simple modifications to the DRAM subarray in order for us to access individual DRAM mats when you are issuing triple activations for in DRAM computation. So those modifications are some isolation transistors and some selection logic. We also extend the circuitry between the I/O interface and the global simplifier with some internet interconnect, which allow us to move data from columns of one DRAM mat to another to neighboring DRAM mats. So on the CPU side, we implement a control unit that transparently orchestrates the computation of process using DRAM operations across different in-DRAM mats transparently from the user. So on the software side, our goal was to transparently extract SIMD parallelism from an application and schedule process using DRAM instructions across the different DRAM mats while maximizing utilization. So to this end, we propose and roll down 3 LLVM compiler passes responsible for code identification, code scheduling and data mapping, and code generation. So the first pass is responsible for code identification. So here we are reusing LLVM's loop auto-vectorization engine to vectorize instructions in loops, plain C loops that can be later on mapped to process using DRAM operations. We also did some modifications to the native loop auto-vectorization engine in LLVM in order to always maximize, always vectorize instructions to the maximum possible vectorization factor based on a loop trip count, and also remove some instructions that are not useful for process using DRAM operation, like load and stores, because you're never loading and storing data when you're executing directly on top of the data stored in DRAM. So the second pass is responsible for code scheduling and data mapping. Here, after generating the loop, the vectorized instructions, we generate a data dependency graph of the vectorized instructions to figure out which instructions are dependent of each other and which ones are not. Then we add some metadata to such data dependency graph in order to tell later on the hardware units which instructions needs to be executed in the same set of DRAM mats, because they have dependencies between them, and which instructions can be executed in individual DRAM mats, because they have independence across them. We also add data movement instructions if there is a dependence from one instruction that was executing one given mat and later on needs to be moved to another DRAM mat. So finally, the final pass is responsible for code generation, and here basically we modify LLVM's x86 backends to generate processing using DRAM instructions in the application binary. So in the paper, we have many other system supports that we enable for all of this to work well, including instruction set architecture, data coherence, data transposition, where I mentioned earlier, address translation, data location alignment, and metadata translation. I'm going to, I thought that I had a slide here. I don't have. One key thing that I forgot to add to the slide here, but it's very important, is data location and alignment, because now I need to make sure that my data in my input arrays are aligned to the boundaries of different DRAM mats, which I don't have the ability to do so from the application side. In order to do that, we create a new memory allocator routine called PIM memory align that is based on huge pages, which allow us to allocate contiguous physical frames and also reverse engineer information for us to figure out which bits in a frame translates to in DRAM rows, banks, columns, subarrays, and mats. So we evaluate all of these in simulation using the G5 simulation for those 12 real-world applications that I mentioned earlier. So here is the CPU normalized performance per watt, and then we see that compared to the CPU, SIMDRAM, which is the prior process using DRAM system, or MIMDRAM architecture significantly improve energy efficiency because we are fully exploit the parallelism available inside the DRAM subarray, so we're not wasting anything. Also, we have some multi-program workload analysis where we map different applications to multiple DRAM mats inside that single DRAM bank. And then we see that compared to the prior process using DRAM system using 1, 2, 4, and 8 DRAM banks, SIMDRAM with a single DRAM bank significantly improves system throughput, again, because we are not using coarse grain in DRAM row activation. So I have many more results in your paper, but we invite you to check it out for more details. So is there any question related to MIMDRAM? So if not, we are about to get to the last work. So we start very easy. I'm going to remind you what we did so far. In DRAM, we started with in-DRAM row copy with row clone. We moved to in-DRAM book bitwise operations with ambits and also the work that Ismail mentioned. Then we moved to in-DRAM addition, subtraction, more complex arithmetic operations with SIMDRAM and a more efficient implementation of that using MIMDRAM. And what is missing for us to have a very complete processor or DRAM chip is how the implementation of transcendental functions. So in DRAM row copy and sine, cosine, logarithm operations, right? And we're going to do that using Pluto. So the main problem, as I mentioned here, all of those work that I just mentioned are very comprehensive on implementing different types of data movement, data intensive operations. However, they are not comprehensive enough because they cannot implement transcendental functions very efficiently. So our goal in this work was to extend the support of process using DRAM systems for any arbitrary complex operations. And to do that, we are going to use a very old idea. So instead of using a arithmetic logic unit to perform some computation, we are going to memorize that computation in a lookup table, and then we are going to replace that computation with a memory access to that memorized lookup table. This is not new, but we are going to see how we can implement these lookup table-based operations very efficiently inside a DRAM chip in what we call a Pluto query operation. So I'm going to explain how this works with an example. Let's say that I have a lookup table that stores the sequence of prime numbers, nature of prime numbers, one by one. So the first prime number that you have is 2, the second prime number is 3, the third is 5, the fourth is 7, and they are stored in a lookup table that indexes each one of those with a value from 0 onward. So the first prime number is indexed in ID 0, which is number 2. The second prime number is indexed in ID 1, which is number 3, so on and so forth. And I want to query my DRAM chip in order to return the second, first, second, and fourth prime number. So to do that, I'm going to first create an input vector, which is going to be the indexes that I want. So I want the second prime number, which is index 1, the first prime number, which is index 0, then the second one is which is index 1, and the last one is index 3. And I expect to get 3, 2, 3, and 7. So the second prime number being 3, so on and so forth. So let's see how these high-level structures are going to map to DRAM structures in our DRAM chip. So first, we are going to have input vector, which is going to be stored in a DRAM row buffer from one DRAM subarray. And I'm going to have output vector, which is going to be the output of my computation stored in another DRAM subarray. Then we are going to have a DRAM subarray dedicated to store our lookup table that was pre-computed. And we are going to add it some match logic to match the indexes of the excess rows in my DRAM lookup table to the input vector that was stored in the different DRAM subarray. This match logic is going to control some excess transistors that you're going to allow data to move from the row buffer of the lookup table DRAM subarray to the output vector. So we are going to store inside the DRAM subarray multiple copies of our lookup table so that we can do a lookup table query operations at very high throughput. So let's start our example here. So we are going to start activating each one of those DRAM rows one by one with this Pluto row sweep operation. So we start activating the first row, which is loot index 1. The activation is exactly what I mentioned in the background. It's going to bring the data to the local row buffer. So all of the data is 2. And then the match logic is going to start asking some questions. And all of this happens in parallel, but I'm going to do serially over here. So it's going to, again, the comparison is between the ID that the row address that I'm accessing in the currently row here and the input vector. So am I accessing the first index of my lookup table? No, I'm actually the second because it's indexed by 1. But anyway, yes, I'm not accessing that ID, so I'm not asserting that particular position in the matching logic. Am I accessing the first position of my lookup table index? Yes. So since the answer is yes, I'm going to assert my access transistor that connects the row buffer to the output vector, allowing us to copy the data in that particular position to my output vector. And this process repeats. So am I accessing the second position? No. Am I accessing the fourth position? The answer again, no. Then after all of this is done, I move to the next row in my lookup table, which is index 1. Again, the data is copied to the local row buffer, and the questions are asked again by the match logic, which is going to be true for the first and the second positions. Again, those positions are going to be copied to the output vector, and then I'm going to copy the output 3 and for positions 0 and 1 and 2. Finally, then I move to the next row, which is 2, and there is no match for this particular row. And then finally to the last one, which is row 3, which is going to be a match in the last position, which allows us to copy the data to the output vector. So in the end, in my output vector, I have the output of my query operation, which is 3, 2, 3, and 7, which is again the second, first, second, and fourth prime number in a sequence. This is just one design of our Pluto setup. We'd have 3 designs into the system, which have different trade-offs depending on how you are implementing this matching logic over here. So this design that I just mentioned here is what we call buffer sense amplifier, which adds this matching logic to the DRAM subarray. These have a medium performance, area, and energy efficiency. The next design is what we call gated sense amplifier, which have higher efficiency, but lower performance and energy efficiency. Don't have the figure here, but what this design is doing basically is I don't have the data is output directly into the DRAM cell from the lookup table here. So it's a destructive operation. This is why the area is high, but the performance and the energy efficiency is low. And the final design is gated memory cell. So the data is written directly to the DRAM cell. And this provides the highest performance and energy efficiency by the lowest area. So in your paper, we also discuss several system integration on how we need to generate lookup tables based on C-based plain code, and how we can compile that and generate the sequence of DRAM row activations that are going to generate the lookup table query inside the DRAM chip themselves. And for that, I invite you to check our paper. So we compare Pluto with several applications for that uses those transcendental functions, and then we see that compared to the CPU, GPU, and prior processing near memory system, Pluto significantly improves performance and also performance per area, and also, of course, provides significantly energy savings compared to the CPU and the GPU. So that was Pluto. This concludes our endeavor for processing using DRAM. We started very simple with in-DRAM row copies, moved to in-DRAM bitwise operations, additions, real-world book bitwise operations in commodity off-the-shelf DRAM chips, and finally, lookup table operations. As we mentioned, for the design of all of these using commodity off-the-shelf DRAM chips, we have open source infrastructure called DRAM Bender, which allow you to play with the DRAM time parameter, and a specialized memory controller that allows you to violate the time parameters and perform those operations in your DRAM chips. We also have end-to-end system called PyDRAM, which provides software APIs for you to trigger in-DRAM row copies directly from your application down to the software. And again, all of this is open source and available, and the preprint is available, on archive, and also was published in TACO, if I'm not mistaken. So, as I mentioned earlier in the motivation, all of those operations are not limited only to DRAM. Other memory technologies, as emerging non-volatile memory devices, are also capable of book bitwise operations by implementing similar approaches. For example, this work called PIM-friendly provides some modifications to the sense amplifier of PCM-based memories in order to allow for the implementations of row copies and also Boolean operations. Flash Cosmos, which I mentioned earlier in the first talk as well, shows that we can do multiple sensing operations to implement and or operations inside flash chips. And as I mentioned as well, emerging non-volatile memory devices that are implemented in a crossbar array are capable of performing insert, multiply, and accumulation operations following Kirchhoff's law, which is very attractive for the acceleration of GEM, general matrix of matrix vector multiplication operations commonly used in neural network models. So there's a lot of startups right now coming up with industry-based solutions for this type of chips. And this is just how it works. Not going to get to details here. So this concludes this part of the talk. Something happened to my presentation. Is there any questions before we go for lunch? So if there is no question, after lunch, we are going to move to more conventional systems. We are going to talk about processing near DRAM architectures. And we are going to also have more invited talks. So thank you everyone for joining, and see you doing lunch. Hello, hello, hello. Okay, but this is the second one. Need to the other one. My jet lag started hitting. I am one talk late that I should be. So
I didn't know. I thought you were on pattern schedule.
I am a little bit behind. But I think I'm going to do this.
Do you have backup plan? But not.
Yes, yes, yes. I'm going to do the next two and then you go. It's yours. Is everything fine with the live stream? Yes? It's okay? Okay. So welcome back, everyone. Hope you had a great lunch. Now you're going to shift gears a little bit from all this processing using memory stuff, and then we are going to move to something that is actually being deployed today, processing near memory architectures. As a reminder, now you can think about logic again. So now we are going to design logic and we are going to design compute, but we are going to move the logic closer and closer to the memory arrays themselves for computation using different memory technologies, either 3D stack memories or to the base integration. So many works that we are going to see here have shown that employ such architectures, processing near memory architectures, can be beneficial for many applications, graph processing, mobile custom workloads, neural networks, DNA sequence analysis, databases, and so on and so forth. So at the time, this slide here was mostly to motivate the need for processing near memory because there was no killing application for this type of architecture back when this slide was made, but this is not true anymore. There is a very good motivation to, and you're going to see that several of the real world processing near memory architectures targets our current favorite workload right now, which is transformers. But anyway, we are going to get that there soon. So again, the main idea here is to move computation near the memory chips themselves using different memory technology integration. So if you have a 3D stack memory like HBM chip, we can move the computation to the logic layer of the HBM chip itself, or we can move the computation near the memory controller, or even inside the DIMM of DRAM, a planary to the DRAM chip itself. And you're going to see example of those implementations as we go here in this talk. So all of this is really nice, but you might ask why we've not been doing this so far, right? Why we should do this now in 2025? Oh, I did something. That's weird. There was no power button that I pressed. But anyway, it like the energy just went down. System. Okay, sorry for that. Let me just wait for the system to come back. Like I put my knee on this drawer, and then this drawer. That's crazy. Can you check YouTube if it's fine? Okay. So maybe it was just for us. Okay. I didn't know that it was that strong. But anyway, so why we are not doing this type of design so far, right? Why now that we are designing this, or why we are not designing memory and processing at the same time, because it's very hard, basically. So, and it's very hard for a myriad of reasons. I'm going to cover 3 here, but those are not the only reasons. Those are the more engineering-related issues, but there is a really big problem related to business as well. I'm not a businessman yet, but there is the main problem of who design who and who is going to benefit from what. So if you are Intel and you're not necessarily designing DRAM chips, and out of the blue, Micron decided to put a processor inside their chip, who is going to design that processor for Micron, and who is going to make money if it's a partnership, for example, between Intel and Micron. But anyway, we're not going to get into that detail here, but that is actually a very big part of why it's very challenging to design this type of system. So in the engineering-related problems, the ones that I mentioned here, I'm going to start with the power problem and the area budgets. So here I'm highlighting the 3D stack memories because it's what we have more data for, but this is also true for planar 2D memory chips. So if you have a 3D stack memory, that memory is designed for capacity, yet you have a logic-based die that you can embed some computation. But that basic die over there is not there for you to design computation, there for a reason. The main reason that is there is some of the 5 parameters are moved nearby the memory chip itself to improve signal integrity of the 3D stack memory. And after you have the design of the PHY and also some controllers that are moved to the 3D stack chip itself, there is some free real estate that you can use to design computation. But if you don't want to enlarge the 3D stack chip, that is memory die, or lose capacity from the logic for the DRAM layer that you have in your memory chip, you're going to have to respect that area budget that is free for you to embed computation at. This might change soon because in HBM generation 4, in JEDEC, they already are talking about custom-based logic in the future generation HBM chips, but it is still a bit unclear how that is going to end up, if it's going to be customized based on use or if it's going to be generic. But anyway, regardless, you have to take into account that area budget. At the same time, you have a power limit that is used, or a power budget that is used to power up or to control your DRAM chip, right? And if you add a compute on top of that, you're going, if you don't want to redesign the power control of the memory chip themselves, you're going to abide for that particular power budget, which is quite small. Also, there is a thermal problem, right? And that might be even more problematic because if you have a planar DRAM chip or a 3D stack chip, which is even worse, if you have compute, that compute is going to generate heat, and you need to dissipate that heat out of the chip. And the way that you're dissipating heat from memory chips is using passive dissipation mechanisms. But at the moment that you put something that does compute inside the memory chip, and if that particular computation requires a lot of power and hence going to generate a lot of heat, you might end up having to have more active thermal dissipation on top of your memory chip itself, which we don't necessarily want. There are a lot of research on 3D stack memories on how to design heat dissipation solutions across layers of 3D stack chips, for example, with using specialized materials, but I'm not going to get into details over here. And also there is the manufacturing problem. The way that we are designing memory using one particular manufacturing technology, and we are designing compute using another manufacturing technologies, because those are different processes are optimized for different metrics. So processing is optimized for speed, while memory is optimized for capacity, for density. And if there is this very old work here, but the only the most comprehensive reference that I could find, that shows that, okay, if you try to implement logic with DRAM, you're going to end up with a logic that has lower speed than if you use that same, if you're trying to design the same logic using the CMOS manufacturing process. And the same is true for the other way around. If you're trying to design DRAM using CMOS-based manufacturing, you're going to end up with lower density for your DRAM chip. So that is the trade-off that you need to pay over here. It's 3 high, so it's 2019. Okay. I'm going to the. Okay, perfect. I'm going to update these slides. It's much better than 1999. Yeah, and it's much worse at the same time. So there is also the problem of metal layers that is not mentioned here. That when you manufacture DRAM, you have around 3 to 5 metal layers for you to round the things. And if you add logic on top of that, you're going to probably need more and more metal layers to route your logic design, which is very costly. And memory manufacturers are not very happy to increase that metal layer count. And you're going to see how this impacts several of the industry-based solutions that are available right now for processing near memory as I progress in this presentation. How especially this manufacturing challenge and also the error bodies impacts the design. Okay, so we have done several works in Safari on designing those processing near memory architectures for different workloads, which takes into account those constraints. But when the time comes, that's going to be more relevant. Okay, now that we, as a designer, we know how we can, what are the trade-offs that we need to think of when designing those processing near memory architectures. What are the types of designs that are available for you as in your toolkit? So this is not much different than how you design processors, because this is in the end what you're doing. So you can either have, for example, general purpose programmable cores attached to your memory design. Often those cores are quite simple. They are wimping cores because, again, if you try to design an autofodder engine inside your memory chip, you're going to end up on those power area and thermal dissipation issues that I mentioned earlier. Also, you can design fixed functional unit accelerators inside your DRAM chip, which are more efficient, of course, because you are tailoring the area for whatever function that you want to do. Or you can design more configurable architectures using something as FPGAs or CDRAs inside near the memory chip themselves. And during this talk, I'm going to highlight advances from both academia and industry for each one of those design points. So hopefully you can get inspiration from them. So we start for general purpose cores from academia. So I already mentioned this work here, where we look at graph processing workloads, and we saw that scaling such graph processing workloads using processor-centric approaches are very challenging because of those applications being very memory intensive. Because mostly when you're traversing a graph, you are doing a lot of frequent random memory accesses and very too little amount of computation. So this is an example for page rank, for example. At the time of this work, the HMC architecture was still a thing. This does not exist anymore. It was a consortium with several members, I don't remember, it was several, with Micro and some other people. Prototype this 3D stack memory where we have this logic die and several logic layers, and we could use this logic die to implement some computing. So we used this technology at the time to accelerate those graph traversing algorithms using general purpose in other cores. Those general purposes are very, even though this was targeting for graph processing, since those cores are reprogrammable, we could use them for other tasks as other future works after this work have done. So this is this work. I just want to highlight the usage over here. So more interesting is the work from academia, from this French startup called UpMem. So in 2019, this UpMem startup, which was actually recently bought, I don't know by whom yet, but hopefully they are still going to have this product. Came up with these 2D DIMMs where you could buy, and each one of the DRAM chips have some in other cores embedded risk, like in other cores embedded for computing. So this is a view. This is just what they have. So here they don't plan, at least at the time, they were not planning to completely replace your main memory with those upmem capable DIMMs. They were mostly put in the system as a data accelerator for data-intensive tasks, where we, similar to a GPU, need to explicitly move data from the main processor and this upmem capable memory. And also logic daycare. Again, this the programming model we're going to see later on fairly resemble that of GPU programming, but they don't use CUDA, of course. They use something closer to OpenP program. So my pointer stopped working for some reason. So this is the original system. This is from the original patent that they filed at the time. Is a principle from that. And this is an overview of the system. So basically, we have the DR master interface connected to several of those DRAM chips. And inside each one of the DRAM chip, you have a DRAM bank called main memory, and also the processor and some instruction cache. So another view of the same system is over here, where we have the regular main memory, the host CPU, and several of their specialized PIM DIMMs with many PIM chips. So something's happening here. Anyway. So inside each one of those PIM DIMMs, what we have is a 64 megabyte DRAM bank called MIMDRAM. Also a simple in-order processor, pipelined and multi-threaded, 64 kilobyte SRAM working RAM, and a 24 kilobyte instruction RAM. Inside each PIM chip, they have 8 of those structures, and 8 of those they are called DPUs, totaling 64 DPUs per DRAM rank. So this is an overview of what you buy if you bought one of those systems from UpMem. We recently bought one of them from Safari, but they didn't arrive yet. But anyway, so what you would have in the motherboard would be some Xeon CPUs connected to the regular DRAM memory, and also in the DIMM slide, some of the PIN-enabled memory. And in the current system, in the biggest system that they have around 2,500 of those simple in-order cores embedded to nearby the DRAM banks. So again, this is coming from their patents. What you can see here is inside that one of those PIN chips. And again, we have the main memory DRAM from the DRAM bank, the instruction cache, and the processor pipeline. So they also had some DDR4 interface and some DMA engine that is used to move data from the DRAM banks to the working RAM. So the processor could not directly access the data from the MRAM. All of the data needs to be moved first to the working RAM prior to processing. And there was some control and status signal that was used to interface with the master, which was the main CPU. So inside this processor, for the DPU's pipeline, we have a fairly simple core. So it was an in-order core running at around 525 megahertz. Each one of those core could be fine-grained, so you could run 2,400 threads, and each processor has 14 different pipeline stages. This core here, fairly simple. They could only do integer-based, native integer-based operations. and float point operations were emulated in software. So their CPU ISA was similar, as I mentioned, to RISC ISA. It was not necessarily RISC, but RISC-like. And they have also their SDK and toolchain with LLVM compiler that allow one to write C-like codes, compile this C-like code, and deploy in their DPU architecture. So if you want to learn more about the UpMem architecture, I invite you to check Juan's lecture online, which is quite extensive. And we had done this very extensive work conducted by Juan that he extensively characterized this architecture and generate benchmark suites with some recommendations for programmers that wants to write code for such PIM architectures. So this is the PIM benchmark suite, which was composed of 14 different applications for various domains, and each application have different computing patterns and also different data intensiveness. So the PIM benchmarks is available online, and has been used for several works to highlight and to propose optimizations to this UpMem architecture. So we keep doing analysis, some other talks from Juan. So we keep doing analysis on top of this UpMem architecture, mostly because it was the firstly commercially available PIM architecture that was available for us to do some experiments. So after the work that we did initially with the PIM benchmarks, we kept implementing more complex applications as we learn the key characteristics of the system. So for example, we also accelerate classic machine learning training applications in this system, where we propose some optimizations to try to circumvent the problems of emulated float points and multiplication operations. So such as lookup table-based implementations, quantization, and hybrid precision computation. We usually compare those applications using CPUs and GPUs, and you see some performance improvements depending on the size of the application. Other examples of applications that are suitable for such systems is sparse matrix vector multiplication, transcendation functions, sequence alignment, and homomorphic encryption, and other reinforcement learning applications. And recently we have this paper Impact, where we also implement distributed stochastic descending algorithms in this UpMem architecture. And all of this is available online and also in archive. So this is just for your reference. This is the upload. So I don't know why I broke this down in two, because now the next part is the continuation of what I just mentioned. Is there any question about the UpMem architecture? So hopefully they are still going to be selling them after they got bought by some who that I don't know who was. Let me. Continue here. Okay, so that was examples of general purpose processing near memory architectures from academia and industry. So let's look now at fixed functional unit examples. So Samsung 2021 released their own PIM process near memory architecture. The first realization was called MIMDRAM. They keep changing their name. I don't know which name they are using right now. Every time they release a new paper, they have a new name for that architecture, but the idea is more or less the same. So at that time, what they did is a bit different for what I mentioned, where we are implementing computation in the logic layer. Since they are a memory manufacturer, since they are a Samsung, they can trade off capacity to compute. So basically, they took a HBM architecture and replaced some of the layers of DRAM with layers of DRAM plus some fixed functional units targeting the acceleration of neural network inference. So let's see how this looks. So basically what they have is this programmable compute units inside that logic layer, and each one of those programmable each one of those PCUs are shared between two neighboring DRAM banks. And what they have, since what they are mostly targeting were neural network inference, was a fixed float point multiplier and add units over here, and also some simple register file. The instruction set architecture for this system is fairly simple, again, because of the type of computation that they are targeting. So mostly make, move, and add. And it also enables for very simple control flow with some jumps to predefined locations. So this is just the implementation that they did for that at the time MIMDRAM architecture, and they keep proposing new architectures based on this system, targeting, guess what, generative AI. So in Hot Tips in 2023, they proposed 3 new architectures for different use cases that follow simple examples of simple designs as this MIMDRAM architecture, targeting different use cases of generative AI workloads. So as you might know, generative AI workloads are quite bound in the generation step because they are dominated by memory-bound GMV operations. So this is a figure from their Hot Chips presentation, where you can see that GMV significantly dominates the latency for the generative generation step of this workload. So to solve this issue, their first proposal is called the Samsung HBM PIM architecture, combines HBM chips in IMD GPUs to accelerate GPT inference. So they don't the figure for I don't have the figure over here, but basically it's the same figure that I mentioned earlier for the MIMDRAM architecture, but coupled with a GPU. And they show that they can significantly improve tokens per second if you combine the GPU inference with the HBM PIM chip itself. So they are not proposing you to completely replace the GPU with their architecture. They just want to offload that JMV portion to the HBM chip inside the AMD GPU doing the inference. So that was for their first proposal for server-like processing. And then they also have a proposal for same problem, but now if you want to generate inference on the edge, on the device itself. So the problem that you have here is that you don't have a HBM chip. So usually you have a low power DDR chip, which is quite sensitive to, and the entire SoC is sensitive to battery life. So they propose a similar architecture to the HBM PIM1, where they have their PIM units shared between 2 DRAM banks. And the PIM unit is basically this very similar to what I mentioned earlier. So some multiply and add fixed functional units used to accelerates the GMV kernel. And they show in their paper or in their talk that they can have significant gains in performance and energy efficiency for smallish GPT models. Finally, they have one solution for scale-out systems based on memory expander, the CXL memory expanding, where the problem becomes not only a memory-bound problem, but also a capacity-bound problem, depending on the size of your large language model. So what they propose over here is 2 main designs. One design embeds computation to the CXL controller. They don't provide much details of what this computation actually is. They have a follow-up HPCA paper that shows more details, but I'm not mentioning over here. Or they have a similar solution where they add the computation to the memory chips inside the CXL device itself. And by doing so, since the CXL memory expanders are, guess what, designed for expanding memory capacity in your SoC, they can scale out capacity and also computation for large language models. And their initial results shows that this CXL PIM architecture can significantly provide energy efficiency and throughput compared to using multiple GPUs. So this was the solution from Samsung. Other memory manufacturers also have own solutions for neural network models. So this is the SK Hynix AIM solution from 2022. They also have a follow-up one called AIM-X, which is a little bit similar. But the main idea here, again, is to add some multiply and accumulate units, but different from Samsung. They don't share the units between neighboring DRAM banks. Each DRAM bank has its dedicated processing unit for generative for GenV kernels. They also have a new design that does row clone-like operations to move data across different rows inside that system. So those are the fixed functional unit examples from both Samsung and also SK Hynix. Is there any question related to those? I don't know if you can go and buy them, but maybe if you can call them, I don't know how I would get a hands on those, but they are available. I didn't mention over here, but I was in FMS last year, and also Micron had their own solution for cross-near memory architectures, but they are not very open about it. So there is not much material available. But anyway, now let's move to reconfigurable cross-near memory solutions. I'm going to give one example from academia from our group that uses this CPU plus FPGA boards to have some computation in the FPGA tightly together with the memory board itself. So we use such boards to accelerate weather prediction, which with our design is called narrow. So what we do basically, so we have the FPGA connected to HBM stacks, and in the FPGA logic, we implement the computation that is responsible for weather prediction. And since that all of this is not necessarily the same SoC, it's more like system in package type of solution, we can enjoy higher bandwidth than being outside of that package, hence improving performance, which are the main results over here. From industry, Samsung also have their own solution called IXDIM, where they are using those ERA DIM-based models. So those are load-reduced DIMs, which have this buffer inside the DIM itself. So this buffer is here not necessarily for computation. Is to improve signal integrity and improve capacity in servers, but they can use this buffer space to embed some computation. And the computation that they actually use in this board is basically some reconfigurable logic. So here is the picture of the DIM, and then inside that buffer they add FPGA that can be reconfigurable. And they show some example how this FPGA-like substrate can be used to accelerate recommendation system, where there is a wait, let me go back. So there is a vector sum operation that is offloaded to the system itself. So our follow-up work have used this IXDIM architecture to accelerate other applications like sparse length sum and also database operations. And if you want more details on this, I invite you to check our lecture online. So all of these hopefully give you an overview of what is out there on cross-near memory architectures, and also to say that even though this might sound a bit futuristic, it's happening right now. So main memory manufacturer players are looking and designing prototypes for key applications using memory-centric approach. So hopefully in soon you're going to see more and more of those applications targeting hitting the market. If they are already not hitting the market, that we don't know yet, because some of the companies are quite secretive about this. So the next thing that needs to be answered is, okay, I can design all of those different types of cross-near memory architectures, but if there is a new application that I don't know if it would benefit from this type of design, how can I know based on some simple metrics if this application would take advantage of near memory processing? And we try to solve this, answer this question with this DAMove methodology. So what we did basically was a simulation-based system. Here I give the example for 3D stack memory, but you can configure as you want, which allows you to do a first level evaluation of if a target application would benefit from a cross-near memory architecture, either a general purpose one using in other cores, or a fixed functional unit one. So we applied this methodology and the simulation to more than 345 different applications for different domains. And we collect our results in this DAMove benchmark suite, which is available online together with our simulator. If you are more interested on this, I invite you to check our talk related to DAMove. So let's say that you want to do research on processing near memory architectures, especially, for example, the Samsung one, and you don't want to buy the chip. There are simulators available online that allows you to do first level analysis. So Samsung has their PIM simulator for the HBM PIM architecture, and there is another group that implemented a MEM-based simulator, which is very good. Actually, this won the best paper award in HPCS last year, called PIM-later. So those are very good tools for you to do research related to processing near memory architectures. So this concludes the processing near memory portions of this talk. Is there any question related to processing near memory architectures? Okay. So if not, we are going to move to the next talk from Constantina. Did you upload it on the?
Yeah, it works. Oh, I might need to speak louder. Okay, great. Okay, so everyone, we're moving on to the next session in this workshop that targets PIM architecture for bioinformatics. A brief introduction about myself. My name is Constantina. I'm a postdoc in Safari, and I have finished my PhD in Greece in the National Technical University of Athens. My research interest lies in the field of hardware software co-design and accelerated architectures for bioinformatics. So this session is going to flow according to this agenda. First, I'm going to introduce briefly the genomics and the bottleneck they have, the problem we have with data movement bottlenecks, which serves as a very good motivation to show that it is very critical to design algorithms as well as architectures that can tackle this bottleneck and create more optimized architectures for genomics. We will have then a brief overview over works that are also done by Safari that target for PIM acceleration or in storage processing acceleration for multiple steps of the genomics pipelines. So there are many critical applications in genomics that show why it is very important to achieve faster, scalable, and accurate genome analysis. Such examples is uncovering and treating diseases that are linked to genomic variations, altering the genome to solve some fundamental challenges in life, detecting pathogens in the environment, as well as performing rapid surveillance in the case of some disease outbreaks, for example. A typical genomic pipeline will start with a sequencing step. This means that the special machines called sequencers operate on DNA samples and create some small fragments of the original DNA sequence that are called raw signals. The next step is base calling. In this step, we actually convert the raw signals into the DNA bases that we all know, ACGTs. And then we have the read mapping step, which aligns the reads that have been sequenced into their matching locations in the reference genome with the outermost goal to actually reconstruct the genome. There is also often an intermediate step between the base calling and the read mapping that performs a filtering in order to avoid operating redundantly on reads that do not provide us with good results. So there is a significant barrier in genome analysis, and this lies in the form of the data movement bottleneck. So the data that are generated by the sequencing machines are first stored in SSDs or HDDs, for example, and then during the genome analysis, they have to be fetched from the memory or even the disk. So this leads to a very big data movement overhead. that can actually be a very large portion of the end-to-end execution. For example, for the energy bottleneck, it is estimated here that it can take up to 60% of the total energy. An indicating factor for this is the fact that a single memory request can consume from 160 to 800 more energy than a simple addition operation. So the reason that genome analysis, part of the reason that they are suffering computationally is also that data analysis is performed far away from the data. We therefore need to orchestrate the algorithms and the architectures so that we can handle data better, and that we need to design algorithms that can actually fit the processing in memory paradigm. Safari has done a lot of work in this domain, and you can find a lot of material online that can show you how you can leverage processing using memory, processing near memory, and how to program some real PIM systems to create efficient architectures for multiple problems, including genomic analysis. So next, we're going to go over a brief overview of works that have been done that show how processing near memory and using memory can actually benefit individual steps of the genomics, but also more complex workflows that also require a co-design between multiple steps. So let's first start from the base calling step. We can see that PIM can be very beneficial to accelerating the base calling. For example, in this work, Swordfish, we saw that it can have very promising results to use memristor-based computational memory acceleration to get better results for base calling that is based on deep neural networks. Moving on to the next step in the genomics pipelines, we have the filtering one. PIM can also be very much, can enable better execution for the filtering step. For example, here in Green filter, we have fast seed location filtering in DNA read mapping using processing and memory technologies. Now, the Green filter actually has a dual contribution, both in algorithmic as well as architectural side. It presents a very highly parallel mechanism for doing the seeding step of the alignment. However, despite the parallelization, this mechanism is still memory bound because it has many frequent accesses to memory. This makes Green filter a very good candidate to be accelerated by tightly coupling with 3D stacked DRAM. Specifically, we place it on the 3D stacked DRAM, and it can benefit because the logic is very tightly coupled with the memory by using some very high bandwidth interconnects. You can find more details in the respective paper. Now let's move on to one of the most computationally intensive parts of the genomic pipeline. This is the alignment step. Here in the AIM publication is basically a PIM sequence alignment framework that evaluates many different sequence alignment algorithms to show how they can benefit from PIM. So we use AppMem for this evaluation. As Geraldo said, is the first publicly open programmable PIM system. And we use different algorithmic ways to perform the sequence alignment and fine-tune different parameters, for example, the scoring penalties, some heuristics, etc., etc. And we can see that actually performing the alignment on this PIM system brings us much better results than actually doing the alignment on some very high-end systems, multi-threaded servers. So we've seen how it can benefit the typical sequence-to-sequence alignment. Now, what happens when we have sequence-to-graph alignments? In general, when we do the alignment at the mapping step, we have to do sequence-to-sequence mapping. However, it is also very beneficial to use sequence-to-graph mapping because we have the possibility to capture some variations in the human genome and actually manage to take into account the genetic diversity. This makes, however, things more complicated in terms of computation. So by profiling the most used tools for doing sequence-to-graph alignment, we can see that the computational overheads are even bigger, and the alignment suffers a lot from high cache miss rates, as well as the long DRAM latency to bring this data from memory. This is, of course, due to the fact that the graphs have some unpredictable patterns, and you never know how far away its neighbor is and where you have to fetch the data from. So since there are no good accelerators for the sequence to graph alignment, this work has as a goal to create a specialized, high-performance, scalable, and low-cost code design that can do both sequence to graph mapping as well as sequence to sequence mapping. And it actually achieves that by creating an accelerator and placing it very near memory, and specifically HBM memory. So we can see here that we create 8 instances of our accelerator for the sequence to graph mapping, and we place each one of them on one of the channels of HBM so that we can secure that there is independent access to HBM memory and it doesn't interfere with the other channels. So all these accelerators can actually operate in parallel and at the same time benefit from the very low latency of bringing data over from HBM. So far, we've seen some examples of individually accelerating some steps, unique individual steps of the genome analysis pipeline by using processing in memory techniques. Now we will move on to more complex systems and see what happens when we have to accelerate multiple steps of the genomic pipeline. A good example is GenPIP, which targets accelerating both base calling and read mapping by PIM. Okay, so this sometimes, I guess. Something, okay. It moved a lot. Good, okay. So we can see that when we have multiple steps in genome analysis, there is a very large data movement overhead between these steps. Also, there is a lot of wasted computation. For example, some data are actually operated upon in an initial step, and we then discover at a later step of the pipeline that they were not actually needed. So this leads to many redundant computations. This is a very good motivational example for that purpose with some quantitative analysis. So starting from the raw signals, when we do the sequencing, we may end up with a sample that is almost like 4 terabytes. After the base calling, we have 5, 4, 6 gigabytes. And then moving on from the pipeline by doing some quality checks and read mapping, we end up again with 382 gigabytes. So this means that there's a large data movement overhead and that we also have to store this intermediate data while actually doing the computations. But if we look more carefully, we can see that after the read mapping, the read quality control, for example, only 80% of the reads can actually be utilized. And going even further down the analysis pipeline, we can see that another 10% is discarded because it does not lead to any correct mappings. So this means that we have a lot of useless data that is just occupying both storage as well as computational power during our analysis. So even though PIM has been leveraged so far in individual steps of the genomic pipelines, and it is effective for each steps individually, it is not enough, and it actually exacerbates the data movement overhead between these steps. No prior work has looked into this, and it's very interesting to see if there is actually some room for optimizations and improvement. And we can indeed see that when we apply these NVM-based PIM accelerators for the base calling and the read mapping, we have an almost 3 times speed up over GPU execution of the corresponding pipeline. However, if we also assume that we manage to alleviate completely the data movement overhead by using PIM, we can see that we go to 6 times speed up, and we have even further speed up if we also assume that we can actually get rid of the useless reads and useless computations. So this is what GenPIP does. On top of implementing the individual steps inside memory, it also proposes some tight integration of the individual steps within the memory. It creates a pipeline of the base calling and the read mapping. The data are consumed as soon as they're generated. And also it gives us the ability to stop manipulating and operating on a single read if it shows that it cannot lead to good results. So we can see here that if we compare GenPIP with CPU, GPU, and some other PIM implementations, we actually have a speed up from 1.4 up to 40 times. The same thing we can observe for energy. So far we've seen how we can benefit from processing in memory paradigm. However, can we further benefit our designs by doing by processing the data even closer to where it is stored? So this leads us to our next line of works, which proposes some in-storage processing for genomic pipelines. So first, we're going to discuss GenStore. So what GenStore does? Typically, in a genome analysis pipeline, we have some data movements that happens from the storage system to the main memory, to the caches, and of course, then we have the computational overhead. This shows that apart from the computational overhead of genome analysis, there is also a huge data movement overhead. So we need to tackle both of these to actually have a very highly efficient system. To address the first one, which is the computational overhead, there are many solutions available in the literature. This includes some heuristics, hardware accelerators, employing different also techniques and paradigms, for example, GPUs, FPGAs, PIM, etc. And also there are filters that can actually operate on the data set and discard the ones that actually will not lead to any good results. However, these solutions do not address the data movement overhead. So then we move on to the key idea of GenStore, which is to filter the reads that do not require alignment, which is the most computationally intensive part of the mapping, inside the storage system. And we can do this in two different ways. First, we can filter out the exact matching reads. These are the reads that match exactly to the genome, so that they would not need for us to actually do the dynamic programming-based alignment, which is very expensive. So we can filter out these exactly matching reads inside the storage. And then we can also filter out the non-matching reads. These reads would actually lead to a lot of efforts, and it would require for us to check a lot of different possible positions and a lot of different dynamic-based programming execution of this algorithm to actually conclude that they are no use to us. So we can filter both of them out inside the storage. This can benefit us in two directions. First of all, we're going to avoid the computation overhead of performing these needless computations down the line. And of course, it also alleviates from the data movement bottleneck overhead of actually fetching them from storage just to discard them later on. And GenStore has actually shown very good results when compared with typical read mapping operations, showing speedups ranging from 1.4 to 33 times, and then energy reduction ranging from 4 up to 30 times. So now let's move on to the next work, which is again in this line of work of in-storage processing. This time, we are targeting in-storage processing for metagenomics applications. So let's go to MAGIS. The main idea is to create the first in-storage system for metagenomic analysis and employ a cooperative in-storage processing that is based on a hardware-software co-design between the storage system and between the host system. Let's go through the MAGIS pipeline first. Metagenomics is actually an analysis that requires for us to identify different species within a DNA sample that includes many different genomes for different organisms. So we would require some input data that is a sample with that includes different, for example, bacteria or viruses. And we also need a large database where we have the reference genomes of these organisms, different ones also. So what we would do is, as a first step, work on the sample and create some input queries, which are like small pieces of this DNA, so that we can see in which organism each of these belong. The next step is to identify if these species are actually present in our sample. And the last step is to calculate the exact percentage, how much each organism is present in our sample. So we can see here the hardware software co-design of MAGIS. The idea behind MAGIS is to perform a very clever task partitioning of the pipeline, and then map each of the steps of the pipeline in some specific parts of the system, of the host and the SSD, so that it can go and be executed on the part that is most beneficial to it. For example, the first step that does the querying, yes, is best to be executed in the host system because of the random accesses that are very much required. However, for the next two steps, we implement some lightweight accelerators inside the storage that can benefit from high parallelism, as well as reading data through the channels in a very high bandwidth. Indeed, then we go on to evaluate Megis, and we can see that we have some very good promising results. It is much faster by like 6 times from a performance optimized state-of-the-art software pipeline that performed this metagenomic analysis. And of course, it's almost 15 times more efficient than the accuracy optimized baseline. We also evaluate Megis in terms of energy consumption and how much energy reduction it achieves against in comparison with the performance and accuracy optimized software baselines and the respective PIM ones. And we can see that we have for the PIM baseline, Megis is 2 times better in reducing the energy. So this concludes here the description of this in storage work. And let's also conclude the session. So what we saw in this brief time is that designing a very efficient system for the bioinformatics is a very critical problem because it can support and facilitate some very critical applications. We have seen that the genomics applications are very much bottlenecked by the data movement, and we need to find a way to create systems that alleviate this bottleneck. Then we moved on to cover some works that even target individual accelerators, individual steps of the genomic pipeline or entire pipelines, and leverage processing near memory, processing using memory, or in storage processing to manage and accelerate both in terms of computation as well as diminish the data movement bottlenecks. Now, many future opportunities still exist. Genomics is a very much growing field. So as the sequencing technologies evolve and new applications arise, we expect that processing in memory is going to still be very critical in creating some very efficient systems to execute these critical applications. So thank you very much for your attention. Do you have any questions? Okay, now we're good. It was too fast. Yeah. Thank you very much, Constantina. Thank you, Geraldo.
Okay, so we have been talking a lot about designs, but what about software? How we actually adopt and program this type of systems, right? So in order to enable processing in memory in current systems, we need to rethink the entire computer architecture step from the application level down to the programming interfaces, system security, reliability, runtime, and infrastructure, because the memory is not designed to trigger computation, right? Or to be an active component in the system. Even though this can be quite overwhelming, we can do that with a mindset shift if we do we trigger each step of the memory hierarchy of the computer architecture hierarchy at a time. So in this talk here, I'm going to show how we solve this programmability barrier for the real PIM architecture for the UPMEM PIM system. So as I mentioned in the UPMEM architecture, in order to program a general purpose process memory architectures as the UPMEM PIM system, the user needs to first split the input data across the different process memory chips in the system, transfer input data from the host main memory to the processing in-memory main memory, manually handling caching inside the memory subsystem of the PIM architecture, and also transfer back the output data from the process memory main memory to the host system. So how does this translate to code, writing code? So let's say that I want to write a vector reduction operation using the UPMEM PIM architecture. So in order to do that, I need to first write code to align my input arrays correctly in the boundaries of a PIM chip, collect input parameter that is going to be transferred to the PIM architecture, distribute the input parameters across the thousands of process memory cores inside the PIM system, launch the process memory computation, collect output results from the PIM cores to the host system, manage the scratchpad memory, and orchestrate overall computation back and forth the scratchpad memory and the processing engines. And in the very end, you as a programmer just want to write 4 lines of code that does an addition operation of a vector to a buffer. The problem here is that programming real-world processing memory architectures like the UPMEM PIM system requires non-trivial effort from the programmer, because it requires the programmer to have specialized knowledge of the underlying hardware while manually managing fine-grained data movement across the process memory cores. So our goal on this work that I'm going to show next is to ease programmability for this UPMEM PIM systems by allowing the programmer to efficiently write process memory PIM code without the need to explicitly manage hardware resources. So to this end, I'm going to show 2 works here. The first one, Simple PIM, and the second one is called DAPPA. So this work, Simple PIM, was presented in PAC 2023. So the main idea here is to provide standard abstractions to build and deploy applications on process memory systems. So Simple PIM is built of 3 main APIs. The first one, or interfaces. The first one is the management interface, which manages metadata for PIM resident arrays. The second one is the communication interface, which abstracts host and PIM to PIM communication. And the third one is processing interface, which provides APIs to generate computation like map, reduce, and zip to implement the target workloads. So let's look at it. Let's look at each one of those interfaces next. So the first interface, the metadata interface, is used for the user to register metadata that's going to be offloaded to the process memory cores. So for doing that, we have 3 main APIs. The first one is the Lookup, which retrieves relevant information from the process memory arrays. The second one is the register, which registers metadata for the target input array. And the third one is the free, which removes the metadata array from the array from the metadata list. Then we have the communication interface. So the first communication interface is called broadcast, which allows the application to move data from an input array to be distributed across the process memory core. So there is a copy of all of the input data across multiple process memory cores. So the second one is the scatter, which does the opposite. So it collects it takes input data and distributes and scatters them around the target process memory array cores. Then you have the gather, which does the opposite, which gathers input arrays from the process memory process memory banks to the host main memory. Then you also have communication across the process memory cores. The first one is the all-reduced communication, which allows a function to be applied to the data across multiple arrays inside the process memory cores, and also the all-gather, which allow the system to compose input arrays scattered across different PIM memory to a unifying array that's distributed across all of the PIM memory themselves. So finally, we have the programming interface. The first one is array, which applies a function across the different data elements of an input array, generating an output array. Then you have a reduction, which applies a reduction function and generates output vector from the output array based on the reduction function that the user passed. And finally, we have the zip, which takes two arrays as inputs and combine the elements of these arrays into a single third array. So on top of that, in SimplePIM, we implement several code optimization routines, such as strength reduction, loop rolling, avoiding boundary checking, function inlining, and adjustment for data transfer sizes in order to improve the performance of the generated UpMem code. So we evaluate SimplePIM using real UpMem PIM cores and 6 workloads from the PIM benchmark suite and previous works that we have done for machine learning workloads. And we compare the hand optimized codes in terms of performance and programming productivity. So just for you to give an example of what we are talking about. So this is a hand optimized code using the UpMem SDK that implements a histogram. And the same code using SimplePIM requires fewer lines, significantly fewer lines of code. And actually, we tabulated the lines of code reduction that we have in SimplePIM in its table here. As you can see, by implementing UpMem PIM code using SimplePIM, we can reduce programming complexity from 3 to 6 orders of magnitude for those workloads. So in terms of performance, because of the performance optimization that we implement in the back end of SimplePIM, we can significantly improve, have comparison performance for 3 workloads and significantly improve performance for other 3 workloads from our benchmark suites for both weak and strong scaling. So SimplePIM is available on our GitHub repository. So then we further improve SimplePIM by further relying on data parallel pattern-based programming in DAPPA. So the DAPPA framework automatically distributes input and gather output data, handles memory management, and parallelize works across process memory PIM cores completely transparently from the user. The DAPPA framework is composed of 3 main components: a data parallel pattern API, data flow programming interface, and a dynamic template-based compilation. So first, the data parallel pattern API is a set of data parallel pattern skeletons that the user used to implement the target computation. So skeleton-based programming is not a new thing. It has been used over the years for parallel programming as multi-program workloads or either also GPUs. And DAPPA provides 5 of those data parallel pattern APIs, including map, reduce, filter, window, and grouping. So the user can combine those 5 APIs in order to describe more complex data transformations. Then we move to the data flow programming interface. So DAPPA exposes the user data flow programming interface, which the main class is the pipeline class, which defines a collection of transformations over the input data. So a pipeline is composed of several stages, where each stage represents one of the DAPPA's data parallel pattern APIs. And data flows sequentially across the different stages. Finally, we have the template-based compilation, which uses templates to generate UpMem related code. We use a template engine called Inge for C++. And similar to SimplePIM, we also provide optimizations to DAPPA's backend in order to optimize performance. The main one here being the collaborative execution between hosts and PIM cores to further improve performance. So let's see how this all works with the example. Let's say that I want to implement a dot product operation here using DAPPA targeting the UpMem PIM cores. So the first step is for the user to select which ones are the data parallel pattern APIs that are going to be used to implement this target computation. Over here, we need a map and a reduce because of the data product dot product operation. Then the user uses those APIs in program the data flow interface, which defines how which operations are going to be executed by each stage. So the map stage executes a multiplication, while the reduce stage implements a sum operation. Note that in this code here, the user does not need to know anything about the underlying hardware. It's only plain C++ code. Then the dynamic template-based compilation takes that this input application that's generated by the user and automatically generates the UpMem PIM binary based on a template of a generic UpMem PIM code and executes that on the UpMem PIM system. So we evaluate the DAPPA framework using real-world up-mapping cores and 6 workloads from the PIM benchmark suite. Again, we use 2 main metrics, end-to-end execution time and programming complexity measured in lines of code. So in terms of performance, DAPPA significantly outperforms hand-optimized implementations, especially because we can have collaborative execution between host and PIM cores for some workloads. So in terms of programming complexity, DAPPA significantly reduces programming complexity by around 94%, since DAPPA does not require the user to write up main related code. Compared to simple PIM, DAPPA provides 3 main benefits. First, it provides a high abstraction level, since the user does not need to manually specify communication patterns in the code. Also, it supports more parallel pattern APIs compared to simple PIM, and further is provide optimizations for collaborative host and PIM execution. So hence you conclude that DAPPA significantly improves state-of-the-art PIM programmability frameworks. So this is our DAPPA works, and this concludes this portions of the talk. So is there any question related to programming the mapping system using such high-level APIs? So if not, we are going to then start some sequence of more specialized talks related to process memory, to the state of the art of process memory. So we are going to have 3 invited talks next, and 1 invited talk from myself from some of the papers that we are going to see during the ICS proceedings this year. So let me get started. With Proteus. So this paper is going to is one of the papers that's going to be presented in the PIM session on Tuesday here in ICS. But if you want to, basically, I'm going to spoil the session. So hopefully you can attend a different session at the time, or attend the same session and ask more questions. And this is a work that is called Proteus: Achieving High Performance Processing Using DRAM with Dynamic Bit Precision, Adaptive Data Representation, and Flexible Arithmetic. So the main problem that you're trying to solve over here is that those processing using DRAM systems that I mentioned earlier in the morning suffers from 3 limitations caused by the naively usage of a bit serial execution model. So the first one is a rigid and static data representation, leading to unnecessary computation. The second one is a throughput execution model, leading to limited latency tolerance. And the third one is the scalability challenge for high precision computation. So then the goal of this work is to design a process memory system that can overcome those 3 limitations caused by the naive implementation of a bit serial execution model. To this end, we propose Proteus, which is a data-aware runtime process using the DRAM framework that dynamically adjusts the bit precision, and based on that, chooses and uses the most appropriate data representation and arithmetic algorithm implementation for the target processing using DRAM operation. So we evaluate Proteus simulation, and you see that it significantly improves performance per area compared to a high-end CPU, GPU, and state-of-the-art system, and also significantly reduces energy consumption at low area cost. So our Proteus infrastructure is available on our GitHub repository. So this is the outline for this talk. So this is the conference talk. So I'm going to skip the background because you already know about processing memory, hopefully at this point, and also about processing using DRAM and how a DRAM chip is organized. So let me go to the problem. Maybe this is an important thing to highlight. So I mentioned early in the morning how we can implement in DRAM arithmetic operations using in DRAM row copies and majority of trees, right? So let's just refresh how this works. So let's say that I want to implement the in DRAM addition operation. I take as input RIP carry adder. I transform this RIP carry adder to only use majority and not gates, because the main operation that you can do in DRAM is majority and not using triple row activation. So let's say that I want to do a vector addition between 2 arrays, array A and array B. And all of these arrays has as many operands as columns inside the DRAM chip themselves. And each element in this array only has 1 bit. So let's see how this works. So after generating the majority inverted circuit here, the system goes through each one of those logic gates and issues triple row activations to the input of those gates. So first I issue a triple row activation to input A, B, and carry in, which is going to be a majority of A, B, and 1, 1, and 0, which is going to be 0 and it's going to be the carry out. Then I move to the next majority gate, which is going to be the majority of carry in bar A and B. A bar, B, and C, which is going to be the majority of 0, 1, and 0, which is going to be 0. And finally, I issue a triple row activation of the previous two majority nodes, which is going to be the majority of 1, 0, and 0, which is 0. So in the end, I have in the DRAM row of carry out 1s, and in another row of some 0, 0. So 1 plus 1 is equals to 2, which is 1 and 0 over here. And recall that the data is stored vertically inside the DRAM subarray. So this is how we do the in-DRAM addition operation. And if you want to do this computation over many bits, so if you have a 8-bit or a 16-bit data element inside your input array, this operation needs to be repeated for as many bits as your data set size requires. Yeah, so to conclude, those processes using DRAM architectures are very wide bit zero SIMD engines. And as we show here in this talk, we can implement such operations in commodity off-the-shelf DRAM chips. So let's talk about the problems of this model. So this bit zero execution model has three main issues. First, it suffers from a rigid and static data representation, leading to subpar performance in the presence of narrow values. This term is going to make sense next. Also, they suffer from a throughput-oriented execution with low latency tolerance, failing to reduce the latency for individual processes using DRAM operations. And third, they have scalability challenge for high precision operations due to this linear and quadratic scaling nature of bit serial algorithms. So let's look at in details of those problems. So it's well known that sometimes programmers store data values with a small dynamic range in data elements with high data formats. So think about it. If you have to store a value 4 or a value 2 in C, the minimum data size that you can use as of a operand is an integer 8, so or a char, right? But the char or the integer 8 has 8 bits. But if I want to store 4, I just only need the first 3 bits. All of the remaining bits are going to be all zeros. The same if I want to store 2. I only need 2 bits represents 2. All of the other 6 bits are going to be all zeros. So this type of feature is called a narrow value. Those being the data which is more dynamic range, 2 and 4 in this example, is stored in large data formats. So this is a well-known feature of many applications. And there are a lot of works that leverage this idea to, for example, compress data in caches in a more efficient way. However, if you use narrow values, or if you take the application that has narrow values and try to accelerate them in bit zero execution model, you're going to end up computing on top of those inconsequential bits, those sequence of zeros here that does not contribute to the dynamic range of the application, hence increasing latency and energy of your processing using DRAM operation. So let's see how this impacts latency and energy for example of addition of A plus B generating the sum. So when I do this, I do those triple row activations that I mentioned in the background. So bit by bit. So first I do the triple row activation for bit 0. This is going to contributes to the latency and the energy. Then for bit 1, and then finally for bit 3. After I'm done with bit 2, I already did the computation for all of the bits that actually are consequential. So those that contribute to my actual output, which is going to be 6. Then after that, I'm just going to compute on zeros. And all of this computation of zeros is adding up to my latency and my energy consumption, wasting the latency and energy for the overall processing using the operation. So we quantified how much narrow values real application have using application analysis, where our main goal was to quantify the amount or they require bit precision in many real-world applications. So here in the y-axis, we have the minimum number of bits required to represent input operands in many loops for 12 real-world applications. And we are going to see the data as a distribution of the bit precisions, where whiskers extends to the larger bit precision and the smaller bit precisions. So we make the key observation that for those 12 real-world applications, they all significantly display these narrow values that I just mentioned earlier. And on average, we can reduce the bit precision for those applications from the standard integer 32 bits to 20 bits on average. In some of our applications, we can dramatically reduce the bit precision even further. The second problem is the throughput-oriented execution with low bit precision. So the main issue that we have here is that processing using DRAM operations are inherently slow because we need to compute over each bit individually for any operand with data width larger than 1. So if you have an addition operation over 2 bits, for example, I'm going to have this inter-bit dependence where I need to generate the carry from bit 0 and propagate this carry to be consumed when I'm doing the addition for bit 1 in a bit serial manner. So let's see how this impacts latency. So let's say that I have a 2-bit addition of, and here I have 1 is 0 and 1. So I want to add 1 plus 1, and I want the output to be 2. Recall again that the data is stored in a vertical data layout in the single DRAM subarray. So again, I need to compute the operation bit by bit. And each time that I do a triple activation, I'm going to increase the latency of the computation. I can only start the computation of the second bit once I generate the carry from bit 0 is generated and propagated to be consumed by bit 1. And after that, I can continue the computation for the operations over bit 1. So the main problem here is that this inter-bit dependence forces the serialization of process-used DRAM primitives because all of the bits are stored in a single DRAM subarray in a vertical data layout. So generating this latency problem. Finally, we have the scalability challenge for high precision operation. So since, again, I'm doing bit precision computation, if I need to do addition over many bits, every time that I add a new bit, my latency and to the precision, my latency and the energy consumption is going to further increase. And this is even more problematic for operations where the bit precision scales quadratically. So the latency scales quadratically with the bit precision, for example, with multiplication, which I need to operate over many bits in order to generate a single output. In those cases, the latency is going to scale quadratically and the energy as well quadratically the bit precision. So to summarize, naively employing a bit zero execution model significantly limits the applicability and energy efficiency of process using DRAM systems for many applications. And our goal in this work is to design a process using DRAM substrate that overcomes the limitations of employing this naive bit zero execution model. To do that, we propose Proteus, but first I'm going to explain what are our key ideas to solve each one of those challenges that I mentioned earlier. We start with the rigid and static data representation. So here, I mentioned this concept of narrow values, but you don't need to accept these narrow values in the computation. We can actually dynamically identify when inconsequential bits happens in your application and perform early termination of the bit zero operation. So in this case over here of this addition, once I compute bits, I finish up compute bits 2, which is the latest consequential bits in the computation. I can terminate the computation of the bit 0 process using DRAM addition operation, hence in saving latency and reducing latency and energy consumption by not operating over those inconsequential bits. To solve the throughput-oriented execution model, we can further enhance the latency of process using DRAM operation by leveraging bit-level parallelism. So as we have inter-bit dependency for this carry propagation here in this header, we also have inter-bit independency because some of those primitives, those 3 majority gates here, does not necessarily depend on the output generated by the first bit. So once the carry dependency is solved, those majority gates here from bits 1 and 0 can be executed concurrently at the same time. But to do that, we need to move the different bits of the data words from a single DRAM subarray to different DRAM subarrays, so I can execute them in parallel. So to do that, Proteus employ a specialized data mapping called 1 bit per subarray, which scatters bits of the data words across many DRAM subarrays to expose bit level parallelism. Also, we leverage inter-subarray interconnect that connects neighboring DRAM subarrays in order for us to move dependent data generated from one subarray to a neighboring subarray. So let's see how this approach can reduce latency for bit serial computation. So again, we are doing an addition of 2 bits. So the first step, we do the first majority gates here in this circuit from bit 0 of my input data. And at the same time that this, after this is done, this generates the carry out from bit 0, which is going to be used as carry in bit 1. Then we use the inter-subarray interconnect to move this carry generated from bit 0 to bit 1 in the neighboring DRAM subarray. After this, I can execute the bit-independent majority gates together at the same time from bit 0 in subarray 0 and in bit 1 in subarray 1, cycle by cycle, further reducing the latency of the processing using DRAM addition. So I'm not going to get into details on how we solve the third problem because it requires further background. But the idea here is to solve the scalability challenge for high precision computation is to use alternative data representation, in particular a redundant binary representation, which uses 2 bits to represent a single data value. So this allows to do arithmetic operations without long carry chains for this particular representation format. So based on all of this, we propose Proteus, which is a data-aware runtime mechanism that dynamically and transparently adapts the DRAM implementation, bit precision, and data format for the input data for efficient process using DRAM execution. So Proteus is composed of 3 main components: a parallelism-aware microprogram library, a dynamic bit precision engine, and a microprogram select unit. So the parallelism-aware microprogram library is a collection of hand-optimized implementations of different process using DRAM operations, each of them having different trade-offs in terms of performance and bit precision, composed of both bit parallel, bit serial, and redundant binary representation-based arithmetic operations. Then we have the dynamic bit precision engine, which aims to identify the dynamic range of evicted cache lines belonging to memory objects targeted processing using DRAM operations. So the idea here is to, every time that we evict a cache line that is going to be used later on for process using DRAM computation, we also register inside the specialized header unit in the memory controller, which is the maximum value stored in this cache line. So these maximum values are going to be later on be used for us to define what is the upper limit bit precision that one might need to use in order to perform the process using DRAM operation. Finally, I will have the microprogram select unit, which identifies the appropriate bit precision of the target process using DRAM operation based on the registered maximum values of evicted cache lines, and identifying which is the most suitable microprogram implementation based on the target bit precision. So if I have a register beforehand that the maximum element in input array A is 7, and in the another input array B is 9, and I know that the process using DRAM operation is addition, I know for a fact that the maximum possible element in this output data is going to be log of 7 plus 9, log 2 of that, which is going to give 4 bits. So independently of the other bits that is inside this input array, I know if I use a 4-bit precision for the target process using DRAM operation, I'm not going to end up on the wasting computation on the error values. So based on this 4 bits information, we probe the parallelism-aware microprogram library to figure out which one is the most efficient implementation of the DRAM realization of the target operation for the target bit precision, in this case 4 bits, and then we dispatch the computation to the DRAM chip itself. So we evaluate Proteus using Gen 5 simulator, which is available online, and we compare it to real baseline CPUs, GPUs, and prior process using the DRAM system. I will use 12 workloads for benchmark suites and two main metrics: CPU normalized performance per area and energy reduction. So I'm going to provide a summary of our results next. So compared to the GPU, the SIM-DRAM framework, Proteus only with dynamic peak precision engine enable, the three-component Proteus framework significantly improved performance per area, especially because Proteus reduces the bit precisions to the optimal or for the target one for the given process using DRAM operation. So we see similar trends compared to the GPU, SIM-DRAM, and Proteus only with dynamic precision engine for energy reduction. And here we make the key observation that Proteus significantly improve energy efficiency compared to such systems. So in conclusion, in this work, we introduced Proteus, which is a data-aware runtime process using DRAM framework that dynamically adjusts the bit precision, and based on that chooses and uses the most appropriate data presentation and arithmetic algorithm implementation for a target process using DRAM operation. We extensively evaluate Proteus, and you see that it significantly improves performance and energy reduction compared to CPU, GPUs, and state-of-the-art process using DRAM systems at low area cost. And Proteus is available in your GitHub repository. So that, thanks for listening, and I will be glad to take any questions for Proteus. Okay, so that's a very good question. So we don't prototype those chips. So what we do is a combination of SPICE level simulations of DRAM cells to figure out what are the latency and the energy impact on doing multiple row activation. And we inject the results of these SPICE simulations back to the Gen 5 simulator. But there is no, the problem is that we don't have a gold model for us to compare the accuracy of the simulator to the hardware, because we are not prototyping those chips yet. Even though we do, as Ismail showed earlier, that commodity off-the-shelf chips can do this computation, they are not designed for this. So it's not also a very fair comparison. So it's all based on simulation and SPICE models. Any other question? If the simulation is very slow, it's Gen 5, so it's as slow as Gen 5. It does not get much better. We don't use full system simulation in Gen 5. It's also system level emulation, so it's not the worst. But a simulation, a data point takes around, I don't know, because I usually trigger a lot of simulations to my servers, and I go home to sleep. Then in the morning they are done most of the time. If I scale the data set to be very large, it can easily take 2-3 days to simulate. Question? Okay, so thank you very much. So let me see if you're going for a coffee break or if you're going for the next talk. It's coffee break time? Okay. Oh, we are a bit earlier. I went too fast. Yes. That's weird. Yes. Okay. So maybe we can just, are you ready to present? Okay, so let's just get the next talk then, and then we can take a longer coffee break afterwards. Yes, I think. That would be the best.
Ready to share.
Here.
Now I think I'm gonna look. I'll just mind what happened.
Like I'm afraid of moving anything and then everything breaking down.
Just like this.
You're muted. And also, I guess
Oh yeah, me too. Yeah.
yes. And also the volume is down for the computer.
Okay. What?
Perfect.
Oh, just a moment. I need. Oh, just a moment, please. Oh. Hmm. Oh, yeah.
So how do you pronounce your name correctly?
Taewoon.
Taewoon.
Yeah.
Okay.
Taewoon Kang. Yeah.
Sorry.
It's okay.
Can
It's
I
hard to
get the
pronounce.
microphone very quickly for me to introduce you? Maybe it's okay.
okay.
Yeah. So you're going to have some invited talks right now. So Taeyong Kang.
Yeah.
Okay. Sorry very much for the pronunciation. So he's a graduate student pursuing a PhD in the Department of Computer Science and Engineering at Korea University. His research interest lies in near data processing and FPGA-based acceleration designs. And his current research focuses on processing memory. So he has a bachelor degree in system semiconductor engineer from a university that I'm also going to budge the name, from South Korea. So thank you very much. And it's also a paper that you might see on the program for, going to see on the program from ICS on Tuesday. So feel free to ask the hard questions here and leave them later for the coffee.
Okay.
Thank you very much. Thank you.
Thank you very much for introducing me to Dr. Geraldo. Right? Good afternoon. My name is Taewoon Kang, a PhD student at Korea University. I'm honored to be invited to give a talk at Memory-Centric Computing Systems Workshop. Today, I will present SparsePIM, an efficient processing in memory architecture designed to accelerate sparse metric spectral multiplication. Sparse metric multiplication, known as SPMB, is a computation involves multiplying sparse metrics with a vector. SPMB is widely used in various fields such as scientific computing, circuit simulation, AI workload, and graph analysis. To illustrate how SparsePIM performs SPMB, we first focus on the outer product computation model adopted in our design. In the outer product approach, each matrix column elements are multiplied with its corresponding vector elements. These produce partial results. These partial results are then accumulated to produce the final output vector. Since our design builds upon HBM-PIM as the baseline architecture, let me briefly review its background. Although this was covered in the earlier session, a short recap will help contextualize our enhancements. Samsung introduced HBM-PIM, also called FIM-DRAM or Alcoable to Excel, at ISCA 2021. Unlike traditional PIM architectures, HBM-PIM follows the JEDEC standard, meaning it requires no modifications to the memory controller. It uses a 32-byte access granularity corresponding to 64 bits per burst length of 4. With this setup, each PIM unit can fetch 16 operands of 16 bits each from the DRAM banks and register to perform computations. Furthermore, while conventional DRAM allows access to only one bank at a time, HBM-PIM enables concurrent access to multiple banks, which greatly improve throughput. HBM-PIM supports a simple ISA with 3 types of instructions. For floating point arithmetic operations, it includes add, mul, mek, and med. For data movement, move and fill are used to transfer data between banks and registers. For control, nope, exit, and jump are available, where jump is used to iterate over a predefined loop. Now let's examine the key limitations of prior approaches in handling SPMB. To reduce memory waste, compression format was proposed. Conventional formats like CSR introduce inefficiencies for SPMB by requiring indirect access to the input vector through the column index array. Because of the irregularity in these accesses, vector elements are often fetched in a non-contiguous and unpredictable manner. As a result, although memory is accessed in fixed size units aligned to the DRAM granularity, for example, 32-byte, in the worst case, only a small portion, such as 2 bytes, may be actually used, while the remaining 30 bytes are unused. This leads to poor data reuse and inefficient utilization of memory bandwidth in sparse workloads. When software optimization is not applied, a simple one-dimension partitioning approach is typically used. The matrix is divided evenly based on the number of columns. However, since this method does not consider the distribution of non-zero elements, this causes some processing units may receive fewer computation and remain idle. So this reduces overall parallelism and leads to inefficient execution. And also, when performing outer product SPMB, each column generates a partial result. However, if these partial results do not share the same row index, they cannot be accumulated. As a result, the accumulators designed to aggregate matching rows is underutilized. This is leading to hardware resource waste. Now it shows how previous HBM-PIM architectures handle SPMB. As mentioned earlier, they do not support indirect memory access. As a result, they must rely on dense matrix formats to perform SPMB operations. To enable this, sparse data must be stored in memory as a dense format, which leads to significant inefficiency in both storage and computation. And command issues from command register and mek operation performed. As shown here, most of the values in the matrix are zeros, and yet they are still multiplied and accumulated by mek units. This means that most of the compute units are processing zero values, leading to significant waste of energy and resources. For example, in the web-based 1 million workload, the number of rows and columns exceeds 1 million, and the sparsity over 99.99%. This highlights the inefficiency of existing architecture when applied to truly sparse workloads. To summarize, the inefficiencies of SPMB stem from three key limitations. First, indirect memory access is not supported in conventional PIM architectures. Second, simple tiling method cause severe load imbalance and result in a low accumulation ratio. Third, there's a lack of hardware support optimized for sparse workloads. To overcome these issues, we propose SparsePIM, a holistic solution that integrates software optimization, a DRAM array compression format, and a lightweight hardware extension to efficiently support SPMB operations. SparsePIM addresses the limitation of prior approaches through three key components. First, we propose a DRAM array compression format draft that fits into the DRAM row and enables efficient SPMB computation. Second, we introduced a software optimization framework based on k-means clustering and non-zero element array refinement. This helps balance workload distribution across processing units and maximize parallelism. Finally, we design a lightweight hardware extension, the BG accumulator, that support concurrent accumulation across multiple bank groups. Each of these components works together to enable efficient and scalable SPMB execution on PIM architectures. First, I will explain how the draft format is constructed and aligned with the DRAM row organization. First, we group 16 values with 16 row indices under a shared one column index. Second, pack seven groups. We also locate a 288-byte buffer region for partial result, 40-byte vector region, and reserved area to match the 1 kilobyte. Finally, the layout is rearranged to align with the 32-byte HBM2 access granularity. For efficient memory access and also fit into 1 kilobyte row buffer size of HBM2. Next is our software optimization bounded cap k-means. Algorithm start by selecting a centroid column. This will be the reference for clustering. Next, compare the similarity between the centroid and the other columns based on their index patterns. Columns with a long distance are excluded, while those with a short distance are grouped together. Then we check the number of non-zero elements in the current group. This process is repeated until all columns are grouped or the number of non-zero elements in group meets threshold. If the grouping finished, we finalize the grouping and assign it to a bank group. This approach forms column groups with high row index similarity, enabling efficient accumulation and reducing index mismatch overhead during SPMB computation. Also, there is an additional non-zero balancing step called refinement. Please refer to the paper for details on the refinement process. Before we talk about architecture and execution flow, I will explain the edit instructions. To support our SPMB execution model more efficiently, we add two new instructions to the HBM-PM ISA. First, the bmove instruction loads data from the DRAM row into the Scala register. This enables broadcast of vector elements for element-wide multiplication. Second, we introduce a BAC instruction, which triggers our proposed bank group accumulator. This instruction initiates accumulations across banks, allowing partial result to be combined in place without returning to the host. Now let's walk through the architecture and execution flow of SparsePIM. Execution begins with activating the row using the standard DRAM activate command. This step brings the corresponding draft into the row buffer, enabling access to the column index, value, and row index field that are packed into the row. Next, the vector value is moved into the Scala register using the bmove command. This operation fetches the vector element from DRAM and places it into the Scala register. By doing so, the vector values become available to broadcast all lanes for the upcoming element-wise multiplication. Once operands are in place, more command issues for element-wise multiplication using the existing SIMD multiplier. Once operand comes from the activated DRAM row, and the other from the scalar register, and multiplication performed. The result of each multiplication is written back to the data register. And now accumulate using proposed bank group accumulator or BGA. First, the index queue is responsible for storing row indices fetched from the DRAM row. This is triggered by BAC command, which initiates the loading of row indices into the index queue. Each BACC command fetches 8 indices from each of the 2 banks. So issuing the command twice allows us to enqueue a total of 16 indices. Note that the process of loading the index queue and performing computation is pipelined, allowing overlap between the 2 stages for better efficiency. Now let's look at the comparator. The comparator checks the row indices stored in the left and right index queues. All indices are stored in ascending order. So by continuously popping the smaller value from either side, matching pair eventually encounter or the EQ's crossover. When both front indices are the same, the comparator pops both entries and asserts the same signal. This signal is sent to register read-write unit to trigger accumulation. Once the same signal is issued, the register read-write unit issues a read signal to the data register in each bank. This triggers both sides to fetch the corresponding data values. These values are then forwarded to the adder controller for accumulation. Next, the adder controller issues the operation to the SIMD adder, which now operates in CST mode to perform scalar addition. The aggregated partial result is then passed back through the register read-write unit to be stored in the data register. And the result is written back to the register. At this point, the accumulated result is written to one side, while the other side is initialized to 0. This allows the host to later identify that this partial result has already been accumulated. After all operations are completed, the partial results stored in the data registers are written back to the partial result buffer using the move command. This process is repeated for all columns to complete the SPMB computations. And finally, the flush controller is responsible for monitoring the index queue. When one side of the queue becomes full, the flush controller triggers a flush operation. We modified DRAM-SIM3 to support SparsePIM execution for measuring performance. As a baseline, we used the Sparse library running on NVIDIA RTX 3090 GPU. For benchmarks, we evaluated 16 SparseMetrics workloads from the Swiss SparseMetrics collection. The simulator and hardware configuration are summarized in tables. Also, our evaluation uses 4 out of 8 DRAM dies, just like in the original HBM PIM architecture. Here are the performance results of SparsePIM. Without software optimization, SparsePIM achieves an average speedup of 1.69 times over GPU. When combined with our proposed optimizations, the performance improves further to 2.16 times on average. In the best case, we observe up to 5.61 times speedup. For detailed analysis and the benefits are detailed in the paper. And now, to quantify how well our clustering balances the workload, we use the standard deviation metric of non-zero elements across the clusters. A lower standard deviation indicates that the non-zero elements are more evenly distributed across the clusters. As shown here, decreasing the delta threshold results in a consistent reduction in standard deviation across all workloads. Delta is a tuning parameter that adjusts the minimum and maximum allowed number of non-zero elements per cluster. By tightening this bound, delta enforces more uniform number of non-zero element distribution, leading to better load balancing. This demonstrates that our software optimization technique guided by delta significantly improves the uniformity of number of non-zero elements distribution compared to the baseline. To quantify how similar the row indices are within a group, we use the Jacquard similarity for metric. After optimization, we observe a clear improvement in similarity across most workloads, meaning that more columns share common row indices. This enables more efficient accumulation and better PIM utilization. Although some workloads show a slight decrease in similarity, the load balance still improves. This is reflected by a significant reduction in the standard deviation of number of non-zero elements. Also, we evaluate the memory efficiency of the proposed GRAF format. As shown in graph, GRAF significantly reduces memory uses compared to previous work. Previous work maps each matrix row to a DRAM row. This causes high padding overhead when the number of non-zero elements per row varies. DRAF packs non-zero elements more efficiently than previous work. On average, it achieves 4.34 times reduction compared to the space-based mapping method, and up to 29.82% less memory uses than the conventional COO format. In the case of web-based 1 million, the memory uses increased because most columns contain only a single non-zero element, resulting in excessive padding overhead. Next, area and power analysis of proposed BGA. We synthesize using Synopsys design compiler with a 14 nanometer FinFET process. The total area overhead of BGA is just 2.21% compared to the baseline HBM PIM's logic includes register file. The dynamic power consumption is 31.85 microwatts, which is about 8% lower than that of existing SIMD multiplier in HBM PIM. To conclude, I will briefly summarize the key contributions and outcomes of SparsePIM. So SPMB is inefficient on CPUs and GPUs due to irregular memory accesses, and conventional PIMs are mainly designed for just dense matrix computations. To tackle this, we propose SparsePIM on HBM-based PIM architecture optimized for SPMB. We also introduced the GRAF format, which aligns with HBM2 32-byte access granularity and 1 kilobyte row size, and apply bounded k-means clustering to improve load balance and processing parallelism. As a result, SparsePIM achieves up to 5.61 times speedup over RTX 3090. Thank you for listening. I would be happy to answer if you have any questions. Oh, yeah.
So the first one is out of curiosity. Did you try using the essential put out there HBM simulator, right?
Oh, yeah, that's right.
Did you try using that?
Oh,
I haven't tried.
I have tried, but I used DRAM Sim 3 because that official HBM PIM simulator is based on DRAM Sim 2. So I think the DRAM Sim 3 is more accurate. So I just used it. To the best of my knowledge, there's another Git repository exists for software set part to adopt to use HBM PIM. Yeah.
Yeah, that was hopefully it was not much room to write down DRAM C3 to do all of this. And my second question, I was a bit curious. Like your results are very good, especially only just the baseline of data optimizations. You already outperforming the GPUs for most of the cases, but there were some few workflows that your hardware only without the optimizations you couldn't outperform the GPUs. And did you know what was specific for those workflows? Because it was very few. I think it was like only 2 or 3.
So you mean?
It's like Spain,
Yeah.
and
Oh.
You know if they have a shared property or something.
So these workloads has some very low non-zero density. So this makes some DRAM overheads, and this cost performance overhead. So in the case of web-based, it could degrade the performance than baseline because of 91.94% of the columns in the matrix contains only a single non-zero element.
Okay, so almost a dense matrix. It's almost dense. It's not still sparse, but like it's only the sparsity is very small. Yes, right? The other one.
But so I can show you some workloads. Almost exponential. They're very sparse, I think.
Yeah, they are.
Oh yeah, that's right.
So thank you very much. So if not, thank you very much again.
Thank you.
Thank you very much. I'm sorry for this. Yes, but not only. Okay, so welcome back. I will have two more talks. The next talk is from Melina. She's going to again talk about one of the papers that's going to be on the PIM session this Tuesday. So feel free to ask the very hard questions over here to Melina. So thank you very much, Melina.
Thank you, Geraldo. Okay, so hi everyone. My name is Melina. I'm a former master thesis student at Safari. And today I will present Mars. It's the first in-storage processing system for raw signal genome analysis. And this work introduces a new architecture that tackles both computational and I/O bottlenecks in executing the raw signal genome analysis pipeline entirely within the storage system by leveraging processing and memory techniques within the SSD. Here's a quick overview of today's talk. We'll begin with background on genome analysis and then continue to discuss our motivation and goals. I'll walk you through the Mars architecture and our key techniques that we implemented, and we'll end with an evaluation of performance and energy efficiency of our design. So genome analysis allows us to understand genetic variation, evolution, and diseases, and thereby also enable breakthroughs in areas like outbreak tracing and personalized medicine. This process of genome analysis typically involves two core steps. The first one is sequencing. In sequencing, we produce raw electrical signals from DNA fragments. And then we have the second step that's called mapping, where these fragments are then aligned to the reference genome to reconstruct a full sequence. Traditionally, a deep learning step called base calling is used to translate these raw signals into DNA sequences. However, the step is very computationally intensive, which is why in this work, we focus on a more recent approach, which is called raw signal genome analysis, also RSGA, that bypasses this computationally intensive base calling step and directly works on the raw input signals. And RSGA enables real-time analysis and leverages the high throughput of modern sequencers that's available. The RSGA pipeline itself has two steps. We have indexing, which happens offline, and then the mapping steps of the raw signals that happens in an online step. In the indexing phase, the reference genome is converted into event representations and stored in a hash table for fast lookup. And then we have the mapping step, which is also in focus of our work, where raw electrical signals are from the sequencing step are then processed into events, hashed and queried against the reference genome to identify matching regions. Mapping itself can also be split into three core steps. The first one is event detection, where the raw electrical signals are transformed into discrete events that represent segments of the signal. Then the second step is the seeding step, where events are compressed into hash values and queried from the pre-built index hash table to find potential matches in the reference genome. And the last step that we have is called chaining, and there we match seed positions and group them to form consistent and also collinear regions that then present the final alignments. So next we'll look at the motivation and goal of our work. So as I already mentioned, sequencing throughput is rapidly increasing. And modern devices now generate hundreds of thousands of signal samples per second, and there's an increasing trend for the future. However, the RSGA pipeline and the software behind that struggles to keep up with this ever-increasing requirements, especially for larger genomes like the human genome that's often in focus of genome analysis. We therefore identified the need for acceleration and started by identifying key bottlenecks in the RSGA pipeline. And here in this graph, on the lower left, you can see the breakdown into the three key steps I just presented, the three key steps of mapping, as well as the I/O data movement overhead for 5 different data sets, with D1 being the smallest genome and D5 the largest one. And we observe here that chaining and seeding, so the last 2 steps, dominate the runtime, while also event detection and I/O overhead are quite significant for smaller genomes. So This actually motivates the need for us to design efficient hardware acceleration and not just focus on compute, but also on the data movement. And to understand the role of the I/O data movement overhead a bit more deeply, we model a scenario where the seeding and chaining step of the RSGA pipeline are accelerated. So here on this graph, on the x-axis, you can see the degree of acceleration that we applied to seeding and chaining. And on the y-axis, it's displayed what the percentage of I/O data movement overhead is compared to the end-to-end runtime of the application. And as you can see, as we accelerate seeding and chaining, I/O quickly becomes the dominant bottleneck and accounts for up to 78% of the execution time, even for larger genomes. And this shows that compute-only acceleration isn't sufficient, but we need to fundamentally also reduce the data movement here. So our goal in this work is to design a high-performance, energy-efficient, and scalable system for raw signal genome analysis by addressing both I/O data movement and the computational bottlenecks. So let's now have a closer look at the actual system we designed, the MARS system. So MARS is the first in-storage processing system for RSGA. And the key idea is that we move the computation closer to where the data actually resides, so inside the SSD. And additionally, we enable processing in memory and paradigms within the SSD to create a highly parallel and energy-efficient system for RSGA. That also allows us to exploit the high SSD internal bandwidth and avoid any host device data transfer. And our design co-designs dedicated hardware inside the SSD with software modification that are targeted towards optimizing RSGA in storage. And we additionally leverage processing using and near the SSD internal DRAM for our design. We optimize the RSGA software pipeline in two key ways to reduce the computational workload and also the intermediate storage requirements. So first of all, we have filtering techniques that are there to discard candidate matches between the raw signal input and the reference genome very early in the pipeline, such that we minimize the computational load by using these frequency and volt-based filters. And second, we also apply arithmetic conversion techniques by applying fixed point representation instead of floating point to reduce the memory footprint and computational cost. And the main challenge in this is that if we apply these changes, that we also preserve the accuracy of our analysis. And we therefore ensure careful placement in the pipeline of both these techniques and fine-tune the parameters that are involved in filtering. We also validated our software improvements, not only improve the performance in the long run, but also and optimize for hardware accelerated execution, but also match the accuracy of state-of-the-art pipelines. And for that, we evaluate the accuracy across 5 real-world genomic data sets. We use the Geraldo base caller and a Minimap2 read mapper as ground truth and compare compare our designs to the state-of-the-art RSGA algorithm, which is called raw-hash2. And we use 2 variants of our design. The first one is MARS CPU float, which is only using the filtering techniques that I just presented. And then we have MARS CPU fixed, which is making use of both the filtering techniques and the arithmetic conversion techniques. And in this results, we basically make 2 key observations. The first one is that our software pipeline actually outperforms recall and F1 scores over the raw-hash2 pipeline across all 5 data sets, so for all different sizes, and matches the precision values of raw-hash2. We therefore show that our filtering techniques are effective in eliminating ambiguous and redundant candidate matches and allow the RSGA pipeline to focus on more informative regions that are then more likely to also present the correct match. The second observation we have is that the fixed point arithmetic actually only leads to minimal loss in accuracy, which is showing that our careful usage of normalization and quantization within the RSGA pipeline ensures that the impact of fixed point arithmetic is minimal. So let's now also look at the actual hardware we implemented. So our design Mars operates in two different modes. We have the conventional mode, where the SSD continues to behave like a normal storage device. And then we also have the accelerator mode, where Mars takes over and executes the entire RSGA pipeline inside the SSD without any host intervention. Let's now have a bit of a closer look at each of the components that make this whole pipeline possible. First of all, we have the Mars control unit, which implements a finite state machine that orchestrates the RSGA pipeline steps, including the control and the data flow. Then also within the SSD controller, we have a dedicated sorter and merger unit per flash controller. So in our design, this would be 8 in total, that can perform highly parallel and hardware accelerated sorting, which is a central step of the chaining step in read mapping. And additionally, we have also placed dedicated accelerators within the SSD internal DRAM. First, we have one arithmetic unit per 2 subarrays, so 256 in total in our design, that performs arithmetic and logical operations that are required for RSGA. And in our design, we leverage a processing near DRAM paradigm that is based on the fulcrum design and leverages DRAM subarray proximity for low latency and parallel arithmetic operations. The second accelerator we place in the DRAM is the querying unit. Here we have one per subarray, so 512 in total. That is used to design efficient in-memory hash table lookups for the seeding step of read mapping. And the design we implement here is based on Pluto that leverages processing using memory to enable massively parallel hash-based or hash table lookups directly within the DRAM. We then go ahead and map the complete RSGA pipeline to the hardware components I just presented and do this as a data-driven pipeline. So we start by breaking down the RSGA steps into really fine-grained tasks like arithmetic, querying, sorting operations, and then go ahead and map each of these tasks to the dedicated compute units that are able to execute them, and thus implement Mars as a pipeline. So for example, if I would have a multiplication step, I would then map it to the arithmetic units that we have in the SSD internal DRAM. And last but not least, we ensure that the complete Mars control flow is then coded into a finite state machine that is executed by the Mars control unit. And for this, we define a predefined execution sequence and dynamically trigger tasks as soon as the input data is available. Before we then jump into the evaluation, let's have a quick look at the Mars workflow and how the data actually moves within the SSD. So we start by loading the raw signal inputs from the flash memory to the SSD internal DRAM to do the event detection step within the arithmetic units we have in the DRAM. We then continue by triggering hash value generation and filtering operations as part of the seeding steps, still with the arithmetic units in the SSD internal DRAM. And then use the querying units inside the SSD internal DRAM to query the hash table, still part of the seeding step. We then continue with chaining, and chaining actually starts with a longer sorting step. So we start by creating batches of sequences, of unsorted sequences, and within the arithmetic unit, and then send them to these unsorted sequences to the sorter units that we have in the SSD controller. And their first short sequences are being sorted by the sorter units, and then these shorter sequences are being merged by the merger units to longer sorted sequences. And we continue the step until we have the final sorted sequences that is then transferred back to the arithmetic units, where the final step of chaining happens, which is dynamic programming, still executed in the SSD internal DRAM, and then the results are sent back to flash memory. And of course, we also have more details on all computational units, the mechanism, also the system integration, and you can find them in our paper. Let's now have a closer look into the evaluation results. We compare our design against 4 other state-of-the-art systems for performance and energy analysis. We use 2 baselines that are based on the base called pipeline. So we have the conventional pipeline that uses GPU-based base calling, and then CPU-based read mapping. And then we also have a hardware accelerated pipeline that's using a design that's called GenPIP. That's based on non-volatile memory hardware accelerated pipeline for base calling and read mapping. We also use two comparison points that are based on the RSGA pipeline. There we have a raw hash, that's a state-of-the-art CPU-based RSGA pipeline. And then we also use our own Mars pipeline, just with the software-only modifications we made and executed on a CPU-based system. For our evaluation methodology, we use a hardware setup with a state-of-the-art server with 2 CPUs, 64 physical cores, 1 terabyte of DDR4 DRAM, and for the base call baseline, an NVIDIA RTX A6000 GPU. For our Mars design, we use an SSD with 8 channels and 8 flash chips each, and it has a PCIe 4.0 interface and uses 4 GB of SSD internal LPDDR4 DRAM with 16 banks and 512 subarrays. For our simulation, we make use of Synopsys design compilers for the accelerator simulation, MQSim for simulating the SSD internal operations, and CACT for simulating the SSD internal LPDDR4 DRAM. So let's now have a look at the performance evaluation results. So you can see here that we again use these same 5 data sets, reward data sets that we already used for the accuracy analysis that have different sizes of genomes. And the graph displays the speed up of all baselines over the CPU-based raw hash 2 baseline. And we make 3 key observations. The first one is that Mars outperforms all other baselines across all data sets. And by outperforming GenPIP, which adopts a processing and memory based acceleration outside the storage, we show that our design is fundamentally able to solve the I/O data movement overhead problem compared to GenPIP. And then last but not least, we also show that our software modifications are able to provide a speed up over the baseline of on average 1.7x. And thereby showing that also the modifications we did are effective in reducing the computational load on our pipeline. We also conduct an energy analysis evaluation, where we show that Mars reduces the energy consumption over all other baselines across all data sets. And of course, these improvements on the one hand stem from the reduced execution time, but they also mainly stem from our storage-centric design that fundamentally addresses the I/O data movement overhead and the energy consumption that comes with this step. Additionally, to our evaluation, we also do an ablation study to find the most suitable system setup of Mars. And we compare Mars against 3 other variants. The first one we use is SparsePIM DRAM, where we replace the arithmetic units with bit serial processing using memory-based arithmetic units. The second one is called Smart SSD, which offloads the sorting step using an external FPGA that's directly connected to the SSD, and thereby replacing the in-SSD logic for sorting and merging. And lastly, we have a setup that's called Mars External that basically uses a conventional SSD setup and implements all the hardware components that we have in our design within the storage, outside of the storage, which means we have, for example, an ASIC near the CPU for sorting and merging. And then we also use a PIM-based accelerator in the DRAM. Similarly, we also do a performance evaluation here. And again, we show that our design outperforms all these 3 variants across all the data sets. And there are 2 more key observations we have here. The first one is that Mars External actually leads to worse performance, mainly due to the high I/O data movement overhead we have towards the storage external compute, which is why it's not able to fundamentally tackle the I/O data movement overhead. And then the second insight, we also have that Smart SSD is not able to reach the performance of Mars, which is mostly because of the limiting factor of the FPGA interface bandwidth. So Mars is therefore the only system that combines the high compute capabilities with a fundamentally addressing I/O data movement overhead, and is therefore leading to better performance results. We also conduct an energy analysis. Here we can now see that actually Mars SIM DRAM achieves the highest energy reduction But maybe just remember from the performance graph, we show that it provides the lowest performance among these ablation variants. And this is mainly due to the usage of the small bit serial arithmetic units that trade energy consumption for performance. We can also see here that Mars external incurs higher energy costs, mostly due to off-chip data movement and also increased host involvement. And we can summarize that Mars provides the best performance energy trade-off between all of these different variants we just showed. So to conclude, we present Mars, the first in-storage system for raw signal genome analysis that's enabled by software improvement and our hardware design inside the storage system. We show that our design matches the accuracy of base calling-based pipelines and improves F1 score over state-of-the-art RSGA pipelines. We improve performance over state-of-the-art software-based and hardware-accelerated read mapping by 93x and 40x respectively, and also show a 20x performance boost over state-of-the-art RSGA software-based read mapping pipeline. Additionally, we show that we significantly reduce energy consumption over all three of these baselines as well, and show thereby that our co-design of software and hardware entirely within the storage system enables real-time, scalable, and energy-efficient RSGA. Thank you very much for listening. Any questions? Yeah. Yes, so we actually don't write to the flash memory during the application. It's like a streamlined application. So we get the data from flash memory, then we operate on it, and then we have the finalized result and we put it back into flash memory. So we just write once when we have the result ready. Okay, there are no more, or yeah.
What's the main reason that you decided to use Chrome instead of other programs?
So we compared against like completely other paradigms, like for example, MIMDRAM, and MIMDRAM is just not providing the same performance benefits as it does with Fulcrum. And the main reason we chose Fulcrum is because it provides a lot of different arithmetic and logical operations that are needed for RSGA. And then it provides a very good trade-off between area efficiency, energy efficiency, and then also performance. So that's why we chose this design. Okay.
Thank you very much.
Thank you.
Okay, so we are going to have our next talk by Professor Sadrosadati. I don't know if she's ready.
Yes, hi, can you hear me?
Muted.
Sorry,
Thank you very much once again for accepting this invitation. Feel free to share your screen when you're ready.
Okay. Is it already shared?
Not yet. Maybe Constantina can make her a co-host again. Okay, can you try again,
Okay.
please?
Yeah, sure.
Okay, now
Okay.
it works. Okay, let me
Okay,
just
awesome.
quickly introduce you. So Professor Sadrosadati, sorry if I'm butchering your last name, is assistant professor at computer science and engineering at the University of California, Riverside. Her research broadly focuses on developing secure, high performance and energy efficient data-centric architectures. She received her PhD from the University of Virginia in 2019 and enjoyed the University of California, Riverdale in 2020. Her work has appeared in top-tier venues, include Micro, ISCA, ASPLOS, and HPCA, Unix Security Deck, ICS, and KDD, and has earned several recognitions, including the NSF Career Award, a Best Paper Award at the ACM Computing Frontiers, the Best of Call Award, and multiple Best Paper nominations, including HPCA 2020, yes, FCM M 2020 and YISWC in 2019. She's also received the Hellman Fellowship and the John A. Stekovich Graduate Research Award. So thank you very much again for joining us here in the Memory-Centric Computer workshops, and feel free to take the stage when you're ready.
Thank you so much for the introduction. Can you hear me okay?
Yes.
Okay, great. Good afternoon, everyone. So my name is Sadrosadati, and I'm from UC Riverside. And today I would like to share some of our recent work and making memory-centric computing more secure and hopefully more programmable. So that this community knows it very well that PIM has evolved from a conceptual promise to a practical architectural directions. And if we want to support PIM in the real world applications, we need to do more than just the raw bandwidth and parallelism. So in this talk, I'm going to talk about some of our effort from my group and how to enable secure computing and processing in memory architecture using lightweight techniques, and also talking about our ongoing work on a compiler framework that we are developing to support both bit parallel in addition to support bit parallel in addition to the bit serial data layout. So let me first introduce my research group. So currently I have 3 PhD students, Jingia, Sahar, and Nurlan. So the work that I'm going to present today are mainly from the research that I've been working with Jingia and Sahar. So this slide highlights the different layers that we are exploring. So that includes key applications such as cryptographic workload, AI inference. We are looking at the compilation framework that employs techniques such as large language model, polyhedral modeling, and eGraph. And at the architecture level, we have been working on designing both in-cache and near-cache computing frameworks that can be adopted for both IoT devices and also higher-end systems. And also our recent work that's exploring the lightweight techniques so that it can enable secure computing on our PIM architectures. And we have evaluated it on the real world PIM architectures. And this work will be appearing in using security this year. So I'm going to go ahead and start with this work first. So in the standard threat model, so the one thing that we trust is the TEE, or trusted execution environment, on the CPU. So that this TEE creates a secure enclave that it can protect both sensitive data and sensitive code. So even if there is a malware running on the system, it cannot see or tamper with what's inside the enclave. So a well-known example of that is like the Intel SGX, ARM Trustzone, RISC-V, Keystone, and Qualcomm secure execution environment. But everything outside of that, including the off-chip memory or any other accelerators that we are using, is considered untrusted. So that once the data leaves the CPU, it's going to be vulnerable. So an attacker may try to read or modify the unencrypted data. It can snoop on the memory bus, or it can perform attacks such as like cold boot attacks so that it can extract information directly from the DRAM. So that's why if the data is sensitive, it needs to be encrypted before it leaves the CPU, and it gets decrypted when it comes back inside the trusted execution enclaves. So if we are starting using this off-chip memory for computation, both for processing near memory, processing using memory, we are effectively storing and processing this data directly inside the memory. So that includes sensitive data, of course. And here's the issue. So if that data is encrypted using the standard memory encryption like AES, then we cannot compute on it because those schemes do not support computation over ciphertext. So once we enable this in-memory computing in our system, we are first with the plain text inside the memory modules, which obviously creates a new attack surface. And That leads us to the main question, that how we can protect data privacy, confidentiality, and integrity when the computation itself happens inside the memory or near memory. And whatever mechanism we are using, it has to be lightweight, because if the security overhead is too high, then it's going to completely defeats the performance benefits that we were trying to get from the PIM architecture in the first place. So in order to enable data confidentiality and PIM, several approaches can be taken. So the first one is the homomorphic encryption, or HE, that the main goal is to allow you to perform computation directly on the ciphertext, but the issue is that it's extremely slow, so it can be up to 1,000 times slower than as if you were doing the computation directly on the CPU before having it to leave the CPU chip. So another possibility is to bring the processing memory into this trusted execution environment, so that we can expand this TEE into the PIM boundary. And that would allow the PIM to process the plain text securely. But the issue would be that it requires redesigning of this PIM hardware that we are seeing. For example, we need to add this root of trust, secure booting, etc. And of course, technically it's possible, but it's going to be very expensive and complex. So in our work, we are taking the third approach, which is using the secure multi-party computation, so that we split the workload between the TEE and the processing in memory module that we are using. So specifically, we are using the arithmetic secret sharing combined with counter mode encryption mechanism. So in this example that you are seeing here, share 1 stays on the trusted CPU, and share 2 is sent to the PIM module, and PIM module can compute on its own share, but it cannot learn anything from the actual data. So that means that we protect against several of these attacks, including the bus snooping, cold boot attacks, and unauthorized accesses. Okay, so as I mentioned, our proposed techniques is leveraging both arithmetic secret sharing, insecure multi-party computation, in combination with the trusted execution environment on the CPU. So I'm going to explain it using a simple example. So in this example, I'm going to explain data confidentiality, like how we are enabling it, and later on I'm going to explain how we enable verification and integrity checking. So assume that we are going to perform computation on the Z on an in-memory architecture. So the assumption here is that X and Y are secret, and there are the member of integer ring, and then the W here is the word size, and then A and B are the public coefficients. So we assume that data is initially encrypted in the memory, in the DRAM module, and so first the data is read into the TEE, and it gets decrypted. And then using the TEE counter mode encryption, we generate this one-time pad using the memory addresses and version number. So those are fixed. And then using the arithmetic secret sharing, we create this ciphertext XC and YC by subtracting the plain text from this one-time pad. And then what we do is that we send this ciphertext to the PIM module to compute a part of the output. And then, so the CPU, the trusted CPU, is going to perform the same computation using the one-time pad. And after the computation is done, the result is going to be transferred to the PIM, from the PIM to the TEE, and they are going to be added with these partial results on the trusted execution environment, so that we can generate the final result. So as we can see, like the final result is going to have only one addition on the critical path, which is going to be very negligible in terms of the overhead. So another thing to note that is that by sharing only by sending only one share of the secret to the PIM module, so if the PIM module is untrusted, it's not going to recover the original secret. So as we can see, both CPU and the PIM module are doing exactly the same computation. But of course, the challenge here is that the CPU has limited memory bandwidth and is very good at doing the compute-intensive workload. But on the other hand, the PIM module has relatively limited computing capability compared to the CPU. And that makes the issue with the workload balancing, and potentially it makes the CPU to be on the critical path. So in order to deal with this problem and to balance the workload between the CPU and the PIM module, in our work, we are applying two approaches. So the first approach that we are employing is that we are having these one-time paths to be generated on the fly using the version numbers and the address, so that we can perform the TE computation on the partial data without the need to bring these secret data from the system memory to the CPU, which, like, that data communication for the TE part is going to be the main bottleneck of the computation. So we are having all this one-time path computation on the fly, so there is no need to access the CPU memory. And that, of course, avoid the communication, the costly communication between the DRAM and the CPU. But still, we need to bring the public data to the CPU. So this approach works very well when the amount of secret data is much larger than the public data. So, and the other approach that we are employing, so if the amount of public data is larger than the secret data, so we are employing this pre-computation method so that we are pre-computing this one-time path and offline, and we store them into the memory. And that, of course, is going to eliminate the computation on the CPU portion for the secret at runtime. And as a result, it doesn't make the CPU to be the performance bottleneck. And again, so that's going to work very well when the public data is much larger than the private data. So let's discuss, like, this solution a little bit in more detail. So the first solution that I'm going to explain here is the runtime version that means that we are doing the computation on the one-time pad on the fly. And based on our experiment, it's going to perform best when, again, the size of private data or secret is significantly larger than the public data. So in the initial stage, the ciphertexts are generated on the TEE by subtracting them from the one-time pad. And then after that, the results are stored in the system memory. At the runtime stage, these one-time pad are generated on the fly, so we do not bring them from the memory. And then the partial results are computed on the CPU. And at the same time, the ciphertext will be transferred from the CPU memory to the to the PIM module that we are working with. And then the computation is done concurrently with the CPU side. And then after that, the PIM module is going to send the result back to the CPU, and this way the CPU will not be in the critical path. So in this scenario, the only thing that will be on the critical path is going to be the only one addition that's going to generate the final result. So on the other hand, when the amount of public data is larger than the private data, which necessitates the communication between the DRAM and the CPU, it means that the CPU portion is going to be on the critical path, and it's going to eventually cancel out the benefit that we are getting from the PIM in the first place. So to avoid the issue, we leverage the pre-computation, again, in the initialization stage. The ciphertexts are generated in the trusted execution environment, and they are stored in the memory. And then in the offline pre-computation stage, So the CPU portion is generated, and then the results are encrypted using the conventional memory encryption techniques, and they are stored back into the memory. And this means that this method works only with the public portion of the data when the public portion of the data is known beforehand and it's not going to be updated during the computation. For example, in the scenarios that can be commonly employed is the DNN inference when the inputs are the secret and the weights are the public data, and we can easily perform this pre-computation and the CPU share as the weights and biases are known beforehand. So this way we have this pre-computed and the computation on the CPU side, then it's not going to be on the critical path. And then at the runtime, so the ciphertext is sent to the PIM module. At the same time, the CPU is reading the result for the CPU portion. The result has been pre-computed already, and then it decrypts it, and that means that the result can be quickly ready to be combined with the result that we are getting back from the PIM module. And yeah. So for the verification scheme, we employ the MAC, which is the message authentication code, so that we can verify the integrity of the data and computation, make sure that the data computation are not modified or they are not tampered with. So in order to do that, we use this linear checksum or the hash function, so that we can generate the tags, and then we can encrypt the tags based on the data confidentiality scheme that we are using, and we store them in the memory so that we can use it later for the verification. So for example here, let's assume that this matrix is our plain text, and the data needs to be protected, and we generate this linear checksum, one per column. And then we encrypt these tags in the TEE, and then we store them into the system memory. And then similar computation will be done on the tags. So after performing the linear checksum over the result, we can compare the new tag with the retrieved tag to verify the results. To evaluate our data confidentiality, integrity, and verification schemes, we are using the Optimum server, which has 20 PIM-enabled DIMMs, 160 gigabytes of memory, and more than 2,500 DPUs. So the host is the CPU. The host CPU is the dual-socket Intel Xeon processor, and we are experimenting on for different workloads. So we are DLRM. We are taking the base code from a UBC group, MLP, logistic regression, and linear regression. We take the base code from the Safari group. So in the performance experiments that we are doing, so I'm going to just talk about the MLP. So in the experiment, we compare our solution with, so we call it Optimum Secure. We compare our solution against 4 different configurations. So the first one is the CPU version. It's a vector-based implementation. And so that's going to be the basic version that runs on the CPU without any security measures. And then we are having this CPU secure implementation that we leverage the TE, Trusted Execution Environment, for the CPU secure. And then we are having this Optimum Insecure, which is the implementation on the Optimum, but applies no security. And then we are having this Optimum Secure runtime and Optimum Secure pre-computation. So let me show you. So the runtime and the verification. So what we are seeing here is that the pre-computation scheme performs best and achieves up to 15 times the speed up over the CPU baseline. And when we are comparing this optimum secure with optimum insecure, so the baseline version of the optimum, we are having only 4% performance penalty. And that means that our security scheme is lightweight and only adds a minimal overhead compared to the baseline optimum PIM implementation. Also, what we are finding is that the verification overhead is very negligible. So you can find more information about our implementation and the result of other applications in the paper or in our GitHub page. So let me wrap up with a few takeaways so we know that the security is becoming a first-class citizen in the PIM space, and as we're getting closer to the deployment, even in the especially in the cloud, so the privacy and trust is not going to be optional. So we need to have a built-in scenario for that. So one of our key contribution is the combination of MPC with the pre-computation, which gives us impressive speed up and very little overhead compared to the baseline optimum implementations. We are also employing to switch between different MPCS schemes so that we can securely support both linear and nonlinear operations so that we make it flexible enough for real-world workload in machine learning and other applications. And for integrity and verification, we are using the linear checksum that has very low overhead, and ultimately, hopefully, this approach can enable low overhead secure computing and real-world PIM hardware without sacrificing performance or practicality. So another work that I'm going to talk briefly, so that's a in-progress work about our effort in developing a processing in memory compiler. So one of the approaches in the PIM library, so I'm sure that it's been discussed a lot during this workshop, is the bit serial model. So the idea here is that to treat each column in the memory like a tiny 1-bit processor, so that we call it a processing element. And with this setup, so you can run the same instruction across thousands of bits at once, like the super wide SIMD engine. So the bit serial layout is impressive. It works well in a lot of scenarios, but it has several issues. So the first issue is that the cost of data manipulation. So it causes the row overflow. So that means that we run out of rows if we are having multiple operands that are stored in the same column, and we are having a lot of intermediate results. So for example, if you want to do the shuffling or permute elements across a vector, it's a lot of inner vector operations. So you end up doing a bunch of memory accesses and bit rearrangement, which is going to be slow and heavy. So another issue is the mixed precision, which is going to be relatively inefficient in bit serial data layout. So that so all the data is packed like vertically, so that if one operand is 4-bit and the other is 8-bit, aligning them across row becomes messy and expensive, and it requires a lot of shifting. So another issue is the high latency. So that if your application cares about latency, bit serial is going to be slow. So that if you're having 32-bit addition, it's going to take roughly about 32 cycles. Another issue is the underutilization, so that if the application parallelism is less than the parallelism provided by the PIM, so it causes hardware underutilization. Also, the data transposition issue, so that when you are reading or writing from or to the memory, so this read and write needs to be break down into a lot of memory access. For example, when you read a full word, you have to fetch multiple rows and then transpose the bits into, so that you can reconstruct the word, and that can be costly in terms of the time and or the control logic. Of course, there's been a few efforts to fix this issue. So one of the works is the MIMDRAM, so that it addresses these challenges by allowing different parts of the memory to execute different structures, different instructions, so that it's going to be the MIMD model, based on the MIMD model, and so it works really well. But one of the downside is that it requires the specific DRAM modification. And also, the core problem still exists. So the computation within each block is still follows the bit serial layout. Our vision is that to develop a compiler so that we can explore both bit serial and bit parallel options, and then choose the best one for the application that we are running. So that of course, that's a difficult task because there are so many options. There are a lot of choices, which makes the search space to be extremely large. So what we are proposing is a full ecosystem that is highly flexible for PIM architecture, so that we assume that this PIM architecture is highly flexible. It can be configured to operate either bit serial or bit parallel. And then the key innovation here is that automatically, so we propose a compiler called MetaPIM, so that it can automatically manage all the complexity and orchestrates the entire process to achieve the high utilization and low latency. So I'm going to give you a few examples on the benefits where the bit parallel is going to perform much better than the bit serial. So on the left, for a vector storage, so bit parallel utilizes all the column of the PIM. Bit serial would use, in this example, only one, which is going to cause us underutilization. On the right side, the bit serial PIM requires hundreds of rows to store a few variables and their intermediate result and the final results. But the bit parallel stores data word by word, which is far more compact. And that's going to be more practical when we have a large number of variables and we have a lot of inner vector operation. Another examples, again, so the left side is the bit parallel arithmetic, which is going to be natively support processing, let's say, multiplication in a single cycle. So for example, if we are doing a 4-bit addition, for the bit serial, it's going to take roughly about 7 cycles, whereas in the bit parallel, it's going to be only 1 or 2 cycles. On the right side is an example of permutation, which is very common in cryptographic application. So the bit serial is very slow because you need to do a lot of shift across different columns so that we make the operands align in the same column. But these operations in the bit parallel manner is going to essentially have no cost, so that we call them zero cycle operations, because you can simply change the row address. And finally, like it offers better support for the mixed precision, so that the compiler can configure different PIM units to operate at different bit widths simultaneously without any conflict. And it also makes it easier to handle advanced control flows such as iterative tasks. So but the issue and the challenge is the complexity of this compiler, because the optimization space is very large. So the compiler has to decide whether to use bit serial, bit parallel, the bit width that is using, so that how to lay out the data, how to time the computation. To the best of our knowledge, there's no compiler that can automatically does all of that for a high-level language such as C. Okay, so what we are doing is that we are proposing to develop an end-to-end compilation framework that is flexible for the PIM hardware. So it takes the standard C code, automatically navigates it, the vast optimization space, and it generates a highly efficient binary code so that we can fully unlock the potential of the hardware. Okay, so let me skip that and just show an example. So, okay, so let me go quickly with that. So first, what we are doing is that we are leveraging LLM so that it can help us with the source level transformation, so that it can help us to identify patterns in the code, such as loop structure, so that it can guide the transformation towards an affine friendly, so that it exposes more parallelism, makes the code more parallelism aware. And that helps the compiler to better understand and optimize the code for the hardware. So then we are using this polyhedral engine so that it can perform these loop transformations, such as tiling and scheduling, data partitioning for the PIM execution. And this is where we are handling data locality, layout conversion, and instruction slicing across the PIM unit. And then, so it's going to happen for both bit serial and bit parallel. And then finally, we are using this egram optimizer so that we can explore data layout and instruction selection, so that this egraph represent many semantically equivalent version of the program. And then you apply this rewrite rule, so to generate diverse candidate. And then we use this target aware cost model to select the most efficient layout and the instruction sequence for the specific PIM configuration, and that includes the bit width, precision, and performance constraint. And we hope that these layers enable a deep cross-layer optimization that makes PIM more programmable, more portable, and more performant. So just quickly going over the compilation flow. So at the front end, we take CNC++, feed it into the LLM engine, then convert it to, so that we can make it more affine friendly, and then feed it into, converts it to the MLIR. And then we go into the polyhedral engine so that we generate different tile version of the code based on PIM-friendly strategies. And then next comes to the egraph, where we use a modified version of the egraph tool so that we can optimize the code. And here we use the cost model to explore the layout choices, the bit width choices, selecting bit serial versus bit parallel. And then after that, we send this optimized intermediate representation to the LLVM backend so that it generates the final binary. And at this point, we inject some target-specific intrinsics to match the actual PIM hardware we are compiling for. So I'm going to show only one of the results that we are having. So that's the work in progress still, but so in this slide, I'm showing an example from the number theoretic transfer, or NTT, which is a commonly used kernel in cryptographic workloads. So we are focusing on the butterfly state, which has two steps. So one step is data permutation to align the operand, basically shuffling data around. And then the second one is the butterfly operation, which is a multiply followed by an add and a subtraction, so that so the bit parallel, so this permutation is almost free because it's just the addressing operations. But in bit serial, we need to physically move these bits around, and that takes about 200 cycles per operand, so which is a major bottleneck. So overall, one butterfly is taking 21 cycles in bit parallel, versus in bit serial is going to be more than 400 cycles. And then when we are scaling it to 1024 point entity stage, which involves 512 butterflies, then it's going to cost more than 10,000 in bit parallel, versus it's going to cost more than 250,000 in bit serial. So that gives us about 23 times speed up of bit parallel over bit serial. So the main takeaway here is that so in this entity example, we show that how bit parallel is going to handle this computation more efficiently than bit serial, which used to be a major bottleneck in bit serial computation. And this permutation, again, is almost free in bit parallel because it's just handled through a smart address calculation instead of physical data movement. So I'm going to stop here. And if you have any questions.
So thank you very much. I love so much the second part of the talk. Not that the first one it was not good, but the second one hits very hard to the very close to heart. So I have some questions. So first, I want to thank you for using that figure for the bit series addition, because I spent one day drawing that figure and I thought it was useless. And then seeing someone using it is just like, oh, that day was not wasted. So thank you very much for that. Second, for the bit parallel algorithms, did you do do you propose modifications to the DRAM array so you can actually implement the bit serial algorithms, like some shifting network or something like the Drizzle works, or
So we
some
are assuming, so we are not restricting the PIM backend. So we are assuming that there are necessary hardware added so that you can perform both bit serial and bit parallel. So we are leveraging whatever is being proposed for bit serial and bit parallel architecture. What we are doing is that we are enabling this compiler framework. Yeah.
Yeah, that's great. I was just wondering because I have this work that's going to be presented in the ICS that I also presented here, the Proteus, that we actually manually implemented some bit is a, to be quite frank, is a weird mix between bit parallel and bit serial. In theory, is bit parallel algorithms by having this distributed data mapping, and together with subarray level parallelism that allow us to do that at low cost in DRAM. I'll be glad to. So I didn't have the chance to update the GitHub yet, but I'm going to do it before Tuesday, which is the talk. And then over there is the collection of hand optimized bit parallel implementations that we did for arithmetic operations like Congestone adder, Karasubda multiplier, all of those bit parallel algorithms. And hopefully it can be used as a baseline for your work and can be useful for testing the testing the compiler. But I think it's great work. I'll be very happy when you get it published, or if you have a draft at some point to share with me, because I really want to check it, because it feels like if I had 2 more years of PhD in my life, would be the culmination of the end of everything. But it's very nice that more brilliant people are taking over and doing the hard work on making all of those architectures very flexible and useful for real applications. So yeah, I just want to thank you for all of the effort. I know how hard it actually is to do those things for this type of architectures.
Thank you so much for your comment. So yeah, that's awesome to hear that you already have an optimized version of the bit parallel, because we are desperately looking for the baseline so that we can evaluate the performance of our compiler. So that it would be great if you send the link to me so that we take a look at it. And yeah, we do have a draft of our paper, so I will definitely share it with you.
Thank you very much. And then going back to the first work, which is also very interesting. Do you think that I got so excited about the second one and I forgot my question. So do you think that the similar approach can be used to other real world PIM architectures? Because private preserving for cloud, as you mentioned, is very important especially in the age of generative AI, right? So I was thinking if like PIM architectures that are more tailored for such workloads would benefit for such trusted execution or distributed execution between the trusting engine and the generative AI PIM architecture, like Samsung or something else, because it seems quite feasible to do so, right?
Yeah, so technically the same scheme can be applied to any other PIM architecture. So the only consideration is that when you are like splitting this workload between the trusted and untrusted party, so you take into consideration that the part that stays on the TEE does not become the performance bottleneck. Otherwise, you are going to have everything on the CPU and not bother to use the PIM. So I think that's the only consideration. That's the important challenge here. But other than that, the same technique can be applied to other architectures as well.
That's very good. That was my question. Thank you very much once again for the great talk. Is there any question for the audience? Wait, there is, I think, a question from your PhD student.
Thank you for the presentation. I just wonder why in the first work, why CPU secure and insecure, they kind of match each other, because I would expect some overhead in the secure version.
Oh, that's a great question. So for the CPU secure version, we are not using Intel SGX. So what we are using is that we are using these virtual machine-based trusted execution environment that are super efficient, and they don't have complexities that incline-based trusted execution environment such as Intel SGX has. So specifically, we are using Intel TDX, or Trusted Domain Extension, which for some workload, it has a very minimal overhead. But like for one of the workload that we've been looking, so the DLRM, so our experiment, so I didn't have it in my slide, but our experiment shows that the CPU secure is having about like 80% slowdown compared to the CPU so insecure version. So some of the reason that an application might not work well with the VM-based trusted execution environment is that if that application is very like intensive in terms of like the memory accesses, or it's heavy in the IO applications, or it causes frequent like virtual machine exits, then it's going to reduce the performance in the secure version. But in the application that I showed, like it doesn't cause much performance penalties.
Thank you very much. Is there any other question? If not, thank you so much once again for the excellent talk. I'm very looking forward for seeing your future works getting published and deployed. So thank you very much once again.
Thank you so much for the invitation.
So that was the last talk. We end up a little bit earlier than expected. Thank you everyone for joining. Thanks everyone that also participate as a speaker doing this workshop. Was a pleasure. If you have any questions or anything related to the material that was covered here today, is online on YouTube and also in your website. And if you have any particular question about PIM, feel free to fire me an email. I'll be glad to discuss and talk about anything that is related to what was discussed over here. So again, thank you everyone for joining. If you're going to Japan, feel free to stop by and say hi to me over there. And then see you during the main conference during the week. Thank you very much once again.